All right. I'm going to assume
Yes.
we're good. Okay. So welcome, everyone. It's a real pleasure to host you here today. We're thrilled to have a terrific group of participants and speakers. This is a very uh, difficult time for many of us and for many people out in the world. So what I would like to do is take a moment to acknowledge the situation that we're all in. And I'm going to just play this it's a 1 minute, I'm going to just play a minute of this just to put a context into what's going on. Okay. So I want to just keep in mind that we're trying to do this event under a time when there's so much stress going on, and to acknowledge the people who have passed away, the people who are struggling, who are alone, who are going to be called on in the next few weeks, especially all the medical providers, to address this very difficult situation. So with that, and with full respect for that what's going on, I want to move on to what we're doing today, which in the spirit of trying to carry on. And just in a little bit of levity here, this is what it feels like, our reaction to how things are going. I think the United States is finally waking up, but it's been a rather slow process. And also, in relevant to AI, Zach Lipton posted this poll that he put out a few days ago, just saying that on a list of existential threats to humanity, AI is in the top. And so about 2,000 people voted, and they put it fairly low. So I think it's important to put everything into context. All right, so this is our a screenshot of some of the faculty that are participating in Bair, and that's 48 faculty. And if we add up all their students, then we're actually talking about close to 300 or more students and faculty who are part of the Bair Berkeley AI Research Program. I also want to take a moment to really thank our staff who are here with us today, who have worked incredibly hard behind the scenes to make all of this possible. And they all work tireless hours. In particular, I want to thank Angie Abbeel for her heroic efforts to keep this ship running. And I also want to thank Trevor Darrell, who if it weren't for Trevor, we wouldn't be here. And he deserves a huge amount of credit for pulling this effort together, for connecting a lot of faculty who have been working in parallel over the years and bringing them together, and reaching out to sponsors, coordinating myriad of details, technical and practical details to make this all work. And I just want to say we can't thank him enough for his contributions, past and ongoing. Now, the big news is the Bair Commons. Since our last retreat, the Bair Commons has opened, and we're really excited about this. It is on the 8th floor of a brand new building, brand new Berkeley building. We call it the penthouse. The Bair Commons is, and I'm going to show you a video in a second, but it's a fantastic new facility and resource. And here's a shot from the air. think this is the video. Okay, I'm going to play this real quick, and I want to thank Ren and Alyosha and a number of students who put this together.
My favorite thing about Bair is the passion and intensity of the students here and the faculty, and how engaged they are about their interests, and how collaborative the work is here. Often we have students work across groups to truly do something that's transformative.
I think here we have the opportunity to collaborate with different groups, and that's something unique.
My favorite thing about Bair is how many different research labs we have. It lets me learn a lot about different AI areas.
I feel like there's usually quite a few people on each paper, and this allows for like a lot of like multifaceted ideas to be explored, which I really love.
There's such a great collection of students and instructors, students of all levels and ages too, just working on such a great variety of topics, all in one area.
The Berkeley area is a great place to live and work. The weather is fantastic. I'd like to work every day, probably 11 months out of the year. And there's just an incredible rich food, entertainment, and also virtual meeting rooms.
My favorite part about the Berkeley area is all the nature around us.
I really like the hiking, and also I really like how it has more of a neighborhood and family feeling.
We're situated both 30 minutes away from beautiful nature, as well as just 30 minutes away in the other direction from one of the biggest cities in the nation.
There's so many different things to do here, that anything that you think you might be into or anything you don't even know you're into yet, you're going to find it here.
Everyone here is very happy, and that's something I noticed when I went for my visit days. It's just hard to find everyone so happy and excited every day.
The best thing about working in BWW is the concentration of really talented minds. You can just kind of like walk around and overhear conversations and fields that are like closely related to what you're working on, but not exactly your thing. You just get exposed to a lot of interesting new ideas.
Although I think people in other departments are equally passionate about the work that they do, I think that here there's a big focus on just doing things because we think they're compelling and beautiful.
We really do have not a set of islands of individual research excellence, but a tapestry of research projects that span from one corner of AI all the way to other corners of AI. And you can find collaborations anywhere along that range, going from theory to large-scale engineering, to vision, to robotics, and all across those poles.
So that's our new space, and we're super excited to move in there. And of course, just as everything was starting to ramp up, we all had to move out. So it's sitting there idle right now, but we're excited to get back into it. What I do want to share with you is that it is a incredible mecca now for research, and it's going to be a catalyst for lots of new collaborations in the future. And we're very excited to welcome you there in the future. Well, also very important to acknowledge the terrific sponsors that made this possible. And this is the new Bair Commons program, and in particular the sponsors as listed here: Facebook, Amazon, Google, Alibaba, Microsoft, and Samsung. We want to thank them for their contributions. These are the lead sponsors. I also want to thank the other sponsors of Bair who are very active and play a crucial role over the years and continue to play a crucial role. This is the list of sponsors here: Adobe, Intel, Netflix, Nokia, 2 Sigma, NVIDIA, UniCredit, and Verizon. And tomorrow, I also want to acknowledge that tomorrow we'll be hosting Kurt Kreutzer will be hosting the session that will be connected with BDD. And so these are the Berkeley Deep Drive sponsors that I won't go through every one of them by name, but Kurt will acknowledge them tomorrow. All right, so this is our plan for today, and we are right on time. I want to thank you again and pass the baton, the screen, on to Claire, who will take over now. Wait a second, where's my, oh, I have to do that. And Claire, you can take the screen.
Okay, thank you, Ken. Hi, everybody. Let me just share my screen. Share. Yeah, good morning, everyone. So it's an honor to start the program, and thanks so much to Angie and to Ken and to everyone in Bair who set up this retreat and under such challenging circumstances. And thank you to all of you who are attending. It's just a pleasure to start and to talk a little bit about the work that I'm doing with respect to Bair. I'm a professor in Bair, and I think that the biggest impact of Bair on my research and the research in my group has been to bring to really integrate machine learning into the work that we've been doing in control theory. And we've been working for years now in trying to develop learning algorithms for robotic systems and autonomous systems which are safe. And today I'll give you a little bit of an update on that. Okay, so let me turn down that volume. Yeah, so we've been working for years in designing safe collision avoidance and maneuver control for robotics, like this quadrotor here that's flying in a room where there are some disturbances. In this case, it's a wind disturbance. And so this sort of falls in the class of learning more about environmental effects, about things that are going on that are affecting the dynamics of a system, and then controlling yourself safely in that respect. I think, though, as we move more and more into what machine learning can really do, it's clear that the big wins are going to be in using learning in contexts where you really don't have good models of the system. And so, for example, we've been working, and this is in this middle panel here, this is work that we've been doing for a number of years in collaboration with Anka Dragan's work in modeling human behavior and controlling systems safely with respect to that. So here we have Sylvia, who's a PhD student in my group, and here's a quadrotor that's trying to plan a safe trajectory. In this case, it's not doing a very good job. It's crashing right into Sylvia while she's moving around the lab. What I'm going to talk a little bit about today is this last panel, or this middle panel and this last panel, about how to control systems where there are really aspects of the environment that you don't have a good model for, like human behavior, like unknown environments. How do you maneuver a robot to a known goal when you don't actually know what's in between, the bicycles, the obstacles, for example? Okay, so I'd like to start with this sort of first point of my talk, which is use dynamics and physics and environment models when they're available. So you don't need to learn everything, but really use learning when necessary. And this has been the point of this project that I just mentioned, where we're looking at a navigation task. This robot is, it knows where it is, it knows where it wants to go around the corner here, it knows its goal, but it doesn't know what's in between, and it's using the camera to get real-time information and then control itself accordingly. So this is what the camera sees over here. And this is, this is a task that computer vision has been working on for decades. And the state of the art in computer vision for this task now is to use a convolutional neural net. So we asked the question, how might you take that kind of convolutional neural net, turn it into a perception module, and then fit that into a control loop, which is what I've pictured here, where you know the model of the thing that you're trying to control, the robot here. That's known dynamics. Maybe there's some disturbances, but basically it's known. So how do you blend together a convolutional neural net doing perception with planning and control algorithms? Namely, how do you design the best planning and control algorithms using the models that you have, but integrating them well with perception modules? And we've spent a couple of years now working with Jitendra Malik's group on designing such a scheme for doing this. This is a This is a little video of this, you know, one of the experiments we did. So here the robot, you can see a top-down view in the upper right-hand corner. The robot's in a room and it has to get to a goal out here. It doesn't know anything about what's in between, but it learns that to get out into the hallway, it has to go through a door. That's nothing that we programmed in. That's something that it learned from the training that we gave it using purely simulated information and training. We trained it using optimal control. And it works really well despite things like really shiny floors and glare that would affect a normal camera using, for example, SLAM algorithms. My second point in this is that if you want to think about safety, then tools like, so control theoretic tools like reachability give you a really good way to keep track of safe solutions and safe actions. So here's that same navigation scheme. Here's the robot with its knowing about its model, and it wants to get to a goal, which is around the corner. And it's around the corner of this, the chair and tables. So what we could do if we had a map of the environment was to create an area, gray area where there are obstacles, white area where there are no obstacles, and then we could compute a control map of that. Basically where the unsafe states are the obstacles, and we can represent those mathematically if we had such a map of the environment. We create a cost function, and then we design control laws which basically rule out controls which push you into obstacles. Okay, so we did this. We did this using a parallel sensing mechanism, which was a depth-based camera on which we were running SLAM. And from that, we created this safety verifier, which acts like a filter to the planning-based control algorithm that I showed you earlier. So it filters away unsafe actions. So for example, in that same scenario here, now the robot is, if it accidentally gets too close to the obstacles, which it would do here if it didn't have this safety filter, then the safety filter comes in and pushes it back into a safe region of operation. Okay, so this the interior of this red region here is a reachable set that's computed in real time from the images that the camera is seeing. So that guides it safely towards its goal. Finally, my last point is about humans. So for learning about humans, scalable sources of data helps. If we'd like to be able to create, for example, navigation schemes that navigate around people, we'd like to be able to train these neural nets with useful data about how to react and interact with people. So one of our latest projects, and this is a project which we've been working on in the Google Bair Commons in conjunction with Alexandra Faust at Google, is this human ANAV. So human ANAV is a new database and a new database for training neural nets, which builds on two databases that exist already. One is the Stanford Large Indoor Spaces set, which we use to train our original neural net that I showed you. And the second is this Surreal database, which is created by folks at Oxford and INRIA, which provides human models that you can place into environments. So we combine these together to make a database which takes the current robot state, takes the human state and control, so you can input this where you want to put a human, a simulated human, in your Stanford Indoor Spaces database. And that, you know, not only the direction, the position direction, but also the velocity of that person, and also information about the person. You can specify gender, texture, body shape. And then this tool that we've developed will put a human into a simulated human into that space, following the particular trajectory that you specified. So what comes out is a set of data that you can then use for training and for testing such neural networks. So you can put humans, and then you can place your robot. You can make the human follow certain trajectories. And in particular, you can you can specify certain cues. So the faster the person is moving, which is specified by the person's velocity, the wider apart their legs are as they move. So these sort of cues prove really important for the robot as it's moving around people. Okay, so this is our old network before we trained it with humans. And here's Varun walking, and he suddenly goes in front of the robot's path, and the robot crashes with him. So now, as we've developed this new dynamic humans version of our network, let's see what happens. So here's Varun. He's going to follow the same trajectory. The robot's trying to do the same thing. The robot sees Varun, sees the way his legs are moving, and moves around him accordingly. Okay, so just to summarize, we've been working now for a number of years on navigation tasks where we're incorporating perception into the control loop. We've been working on real-time updates of reachable safe sets used as a control filter. We've been developing models of human motion. And then as we move forward, we're working on a number of tasks within my group. For example, under the auspices of assured autonomy, we've been developing tools to verify learning-enabled components in the control loop. So I'd like to conclude just by thanking a whole bunch of students who've been working on this, our funding sources, and in particular, I'd like to thank Alexandra Faust at Google. This project in the Google Bair Commons has been really instrumental in particular in that in the latter work that I showed in incorporating simulated human models into our training sets. Thanks very much, and happy to take any questions if there's time.
Thank you, Claire. Thank you so much for staying right on time. Perfect. So we can do, I also want to mention that there's a way to respond if you would like to raise your hand. If anyone does that, I'll be able to see that and respond to you if you have a question. Claire, while we're waiting for that, can you say a little more about the last thing you mentioned, name of the project with Google under the Google Commons program, and as you mentioned, getting the human into the loop. In other words, how is that interaction going?
Oh, it's well, it's been great. So we've been working for about I guess about a year now with Alexandra, and this has really been on this HumanNav database that we've created. So we've been meeting, basically weekly or bi-weekly with Alexandra and her group, and she she's been giving us great advice. She has a lot of expertise in this area, but she has also given us access to the computational facilities at Google, which have made this project go much faster than it would if we had only restricted use of what we have at Berkeley. So not only intellectual collaboration, but also computational collaboration.
Oh, great. Actually, that's what I was curious about. So this is with Google Cloud credits, or are there other resources that you're using?
Yeah, we've been using their Google Cloud servers, which are lightning fast to compare to what we have at Berkeley. So yes. Great.
Okay, good. I'm not saying a flood of questions here. I think everyone's getting used to this new interface, but I do see one. Sandra Scaff. Sandra, great. Allowed to talk. Unmute. Sandra.
Hello. Hi, this is Sandra. Do you hear me?
Yes.
Yeah. Yes.
Yeah. So I wanted to follow up a little bit on the computation aspect. So are these using GPUs or GPUs?
They're using Google. I think it's GPUs. So the cloud credits that we get are using Google's GPUs.
I have a feeling I know why you're asking that, Sandra. Sandra's from NVIDIA. Sandra, is there anything you want to add? We're gonna switch over to Shankar in a moment, but Sandra, anything you'd like to add about developments at NVIDIA?
Yeah, I would just, I actually have a question again about the simulation of the humans. Is there any particular software that you're using for simulation?
No, so we're basically the planning. So there's two databases that we brought together: the Stanford Indoor Spaces database and the Surreal database. And then we did a lot of the work behind the scenes, using fairly standard planning and control algorithms to plan paths for both the person. So the person's path is stipulated by us for training, and then the path of the robot is determined using the neural net that we've been training. So that's trained using optimal control, in the sense that we have a planning algorithm that provides a spline-based planner, and then a linear quadratic regulator that guides the robot along the path that's planned.
Great.
Okay.
Thank you. Thank you. Okay, thank you, Claire. I want to give you a round of applause as best we can here with the applause symbols. Thanks for a great talk. All right, Shankar is up next. So Claire, if you close your screen, end your screen.
So I stop share.
Stop sharing. Very good. And then Shankar, you should be able to share yours. And should we make sure we unmute Shankar? I see him on the list. Allowed to talk. Promote to panelist. He's there. Okay, and let's see.
All right.
Oh, beautiful. Okay. Welcome, Shankar. We're excited to hear from you.
Let me just thank you. Is that what I should do? Yeah.
You can do.
All right.
Beautiful.
I'm not going to presentation.
You've got some good AV support there.
Okay, Ken. I'm ready.
Thank you, Shankar. Go ahead.
Okay. It's really a tribute to all of you to have run this meeting. I want to tell you about a project that's just building up steam. Perhaps you'll hear from Mike, Jordan, and others. A lot of us have been interested in how it is that this confluence of AI, cloud computing, the talk about GPUs as well as edge computing, so you had in deference to our colleagues at NVIDIA, is really changing how we live. And, I think that Ken put up this picture about, AI as an existential threat. I have a rather different view of this. I think that it'll take a lot to incorporate all of these advances in AI and machine learning into our societal systems. And I think that seemed like a slightly unstable connection. Is that on my part, or? Okay. So I think that what will happen is that not only should we pay attention to providing services, but we really need to think about how it is that users will respond to automation. So just to give you an example, we all have experience of using roadmap things for planning our routes. The question is, when there is a blockage in the route, if everybody follows sort of the suggested deviation, what happens? And we've all been familiar with how when you follow a Waze app or a Google app or something like that, and you go past a place where there's congestion, it actually induces new congestion. And so the question is, how do you model human beings as they take a look at automation? So let me start off with an example from power systems. Actually two examples. One on the left is power, and the one on the right is smartphone usage. So there's this concept of disaggregation. can you take a look at what comes out of a smart meter and using machine learning techniques or identification techniques, can you come up with a linkage of what usage there is on household devices? And the answer to this is amazingly that at high enough frequency of data from the smart meter, you can not only tell what devices are plugged in, but also even which television sets are plugged in. And if it's at a high enough frequency, you can even tell what channels they are. If all this sounds a little creepy, it should be, because there are real concerns that this could, in fact, result in, knowing about the level of occupancy of a house, and just from disaggregating smart meter data. The one on the right is, of course, from looking at cell phone signals, and to be able to then infer motions of people just from tracking, their cell phone signals as registered by local towers. So that's known as disaggregation. And the issues here really are a collision between utility and privacy. The picture on the left shows something which is called demand response. In electrical power, quite often you do want to know details about what people are consuming so that you can advise them to turn off certain devices so as to be able to do a certain amount of load balancing, because that enables you to shave off the peaks in the power. And so the pictures on the left show you really that as you have sampling rates, the first one is uncontrolled, the second one is 1 minute sampling rate of the smart meter readings, the second one is 30 minutes sampling. You can actually control the demand you can respond to the demand pretty much in real time to the supply. And this is really critical for being able to match supply to demand, especially in a world of renewables, where you really do need to match consumption to the production that is there. But of course, it comes at a price, because if you look at the right, you see that from looking at the smart meter data, this is actually just from a standard DOE database, you can not only infer what a person's consuming, but you can also infer their income levels. And so, this is a question of sort of leakage of private information while you're trying to do something is a critical one. So you might ask yourself, can you provide incentives? Quite often it's said you should not have freebies, you should charge people for the data. And so here's a theorem that one of my students, Roy Dong, who's now at the University of Illinois, did, which was to try to see if you could price privacy. So if you can provide electrical power cheaper for people who allow their smart meters to be read more frequently than those who don't, and that's indicated by low privacy setting is high frequency readout, high privacy setting is low frequency readout, and then provide the same electrons at a cheaper price if you opt for one or the other. The logic being that, if the power company has access to more fine-grained data, it can do a better job of supply and demand. Of course, what happens is that if you then try to understand what happens to society at large with such a pricing scheme, you find out that the so-called Nash equilibrium, which is the sort of the competitive collaborative equilibrium, results in high privacy setting individuals free riding over low privacy settings. And this really sort of plays in to a sense in society where low income groups feel that data is being collected by them to be able to benefit people who are not as well off as them. So this is actually a theorem out of, it involves some economics and it involves game theory, multi-person game theory. And so this immediately points out to the fact that as you price services which are based on data analytics, privacy is not absolute. Here's a point of view where we're actually pricing it. But you have to be careful in how you price it, or else to provide side payments to account for this free riding. And so it's critical that we get into doing this as we provide privacy contracts. There's very much the raging debate here about how do you do mechanism design so as to really not have the harsh hand of regulation sort of step in and possibly do things which are not as advantageous. Of course, there is a need to provide regulators with the technical solutions and to work hand in hand with them. So let me sort of lead you through how this, what sort of new science is needed to do this. So this is what we call digital transformation. So digital transformation is really about the market for data. How do you use the market for data, and how do you put it back into the closed loop through analytics, controllers, and incentives? Of course, you've got to realize that users have incentives to obfuscate or strategically manipulate their data. Companies may have to compete for consumers. They may want to use data to improve their competitive edge. And furthermore, there's asymmetric information. And furthermore, there's yet another problem, which are these so-called n-sided markets. This is a term which comes from game theory. It's that when there are a number of players, they have a single game that they're playing. They all have separate utility functions. So-called Nash equilibrium is for that one. But if the same players are involved in multiple games, so for instance, there are drivers and there are passengers in an Uber or Lyft case or a shared transportation case, how do you then sort of simultaneously play multiple games and be able to optimize them? So that in turn is where our methods of AI and machine learning come in. The very first set of things I want to talk to you about is about how do you build plausible models of human behavior? Again, our friends in CogPsych actually are quite non-averse to building models of human decision-making using reinforcement learning, risk-sensitive reinforcement learning, and to come up with models which really use a lot of the kinds of models that we use in inverse reinforcement learning and really sort of standard fare in the AI community to come up with ways of building utility models as well as decision-making models for human beings. One thing that you got to pay attention to is that the word utility, human beings aren't necessarily utility minimizers, utility maximizers. And I'll talk to you about two ways this manifests itself. The first one is that this is a picture from a rock concert somewhere in New York City in the days when we used to have rock concerts. That's not so long ago, but this is a 2015 rock concert. And there are, there's too much data in this picture, but this explains, the green line in the top picture and the blue line, the red dotted line are the number of people calling for cabs in this case. The green lines are the number of drivers that are responding, and the blue lines are the number of passengers who actually take rides. So what happens amazingly is that even if you're not careful about how you price search, or how you price it both for, in this case, a two-sided game. There's a game for the drivers and there's a game for the passengers. It results in only marginal gains for the drivers and a major loss for passengers and a huge number of disgruntled people who don't actually get the rides that they wanted. So that's, that's an example of where mechanism design is critical. The second thing comes from Kahneman and Tversky. These are both Nobel laureates from the Hebrew University who showed that, in fact, human utility functions actually are more risk-averse on gains. That's the upper right-hand quadrant of that picture out there, and are more risk-seeking on losses, in the sense that human beings tend to be more pessimistic about, what they might gain, and they tend to be incredibly sensitive to what they might lose. And losses tend to loom larger than gains. And this needs to be built in when we build cognitive models of human decision makers. And, this Kahneman-Tversky theory sort of puts some tweaks on top of the standard utility maximization, which is a staple of all of AI and machine learning. And so it does need to be taken into account. So some formulas down there for the utility function So it's not insuperable to build in these models around reference values. And again, in the interest of time, let me not dive too much into the mathematics. So let me talk to you.
Shankar, sorry to interrupt, but we are at 12 minutes now, and we have 15 minutes for your session. So I just want to encourage you to
maybe go to the last. I think just two more sentences. The machinery for dealing with this is amazingly something which is perhaps more commonly associated with gambling, called multi-arm bandage. And, in this, it's again something that we're using. These acronyms are what you use, CBR for clicking through choices. UCB is not Berkeley, it's a confidence bound. We need to be able to have these multi-arm bandits be models of consumers as they respond to different incentives. So incentives are everything. In the interest of time, I don't want to lead you through how we tried to take all this with Seattle Department of Transportation data. The issue here was, how do you prevent congestion in the downtown by providing people parking apps so that they can be incentivized to not cause congestion? And it's a very, very interesting story about how you have to strike a trade-off between the city trying to maximize its parking revenues, shopkeepers not wanting more than 70% occupancy rate in front, and they're providing coupons for people to come and shop at their stores. So the technology that goes into this, is work with Lillian Radcliffe, is really how you have to model this data market and how you do the analytics in the cloud, sometimes at the edge, to be able to provide them. And these are, there's some things you got to pay attention to. Strategic data sources are effort averse. We as consumers don't necessarily want to give it. The non-rivalrous and multiple data buyers want data sources to be able to make things advantageous for themselves, but are sometimes not willing to pay for it. And this is the way around, is the incentives to justify it. And so this is my last but one slide, Ken, you'll be glad to know that I think that as you start thinking about how people respond to machine learning systems and how you got to build in their responses. You got to model how they, as people, how their cognitive models change in response to different incentives. And by the way, as you're doing this, take into account really how these user preferences change, how the system evolves. Of course, I feel that this, of course, many, many other uses of AI, but the economic impact of this on societal systems is simply off the charts. And this is a Boston Consulting Group study of what this could do for some of these infrastructure systems. But with that, I will stop. At least it's within the 15 minutes, I hope.
Oh, that's beautiful. Thank you so much, Shankar. This is great. And actually, I'm really glad you mentioned the psychology here, because that's a perfect setup for our next speaker, Alison. So Alison, while you're getting ready, I do have time, and I want to give Claire the privilege of being respondent. Claire, would you ask one question? Hopefully brief, under a minute.
So Shankar, can you tell us about in 1 minute or less, what the plans are for this new Digital Transformation Institute at Berkeley and other campuses?
I'm not at liberty to disclose. There will be a major announcement coming soon, which Bair is at the heart of, if I might say so, which will involve rather a large project along the lines of what I've talked about, which will really bring together policy, economics, and of course, the cognitive models of human beings into response to AI systems. And please stay tuned for Thursday morning.
Great. Okay. Thank you so much, Shankar. I want to, Alison, if Shankar, if you unshare your screen.
Yes, I will.
Then Alison will come in. Thank you so much for this update, and we're very excited about that announcement when it's ready. Alison, are you there?
I'm here.
Great.
It's still saying that. Let me try sharing again. There we go. Okay.
It's nice we get to see everyone's living room.
Yeah. Although I do like yours especially, Ken. This is how we've been coping in our house, is that I'm teaching Abbeel about Star Trek: The Next Generation. So
Oh, good. Okay.
that's been our great cultural development. Okay. Can everybody see this? Can I do this as a presenter view? Do you know?
Yes, it should work. That should work.
Should work. Okay. There we go. Okay, great. Well, thank you all. Thank you all for being here, even if indirectly. And I want to start out with a quote from Alan Turing. Way back in 1950, shortly after Turing made his famous proposal about using the imitation game as a way of the Turing test as a way of trying to tell whether an AI was actually intelligent or not. Right after he says that, he says, but wait a minute, maybe what we really need to do is, instead of trying to simulate the adult mind, what we should be doing is simulating the child's mind instead. And everybody, until pretty recently, sort of ignored that part of Turing's claim. But the great outpouring of learning, the great renaissance of learning in AI, has made people go back to this observation of Turing's, because children, after all, are the best learners that we know of in the universe. We know that by the time they're 4 or 5, with no external tuition, they're learning the structure of language, developing intuitive theories of the world around them. And if we could figure out what it is that they're doing, that might really help us to design genuinely intelligent artificial systems. But when we actually look at what children do, which is what I, as a developmental psychologist, and my colleagues have been doing for a long time, what we see looks very different from the kinds of typical things that we see in AI learning. So in AI learning, as we all know, we need enormous data sets. It's very hard to get the right kinds of generalization, as in adversarial examples. On the other hand, we can do it. It's more or less computationally tractable. If you compare that with what we know about what every little 4-year-old does when they learn, they're learning from relatively little data, and more importantly, data that's very different from, say, a giant image set. The children are learning from the equivalent of a kind of weird video feed of a few toys and moms and dads. There's very little explicit supervision or reinforcement, or even implicit supervision or reinforcement, as those of you who have children at home now will testify. And yet they do excellent generalizations. So from this small amount of data, they can make very good generalizations and generalize in appropriate but strikingly broad ways. On the other hand, even though many of us have been trying for 20 years to get good computational models of this kind of learning, the models that we get are not very tractable. So there are things like Bayesian inference that very rapidly become exponential. So the question that we've been asking is, could we design a system that could learn the same way that a 4-year-old could? Unfortunately, DARPA has decided that this is a good thing to study too. So along with Jitendra and Alyosha and Trevor and a bunch of other people at Berkeley and elsewhere, we've had this grant to try to see if we could design these systems. And one of the things that we learned about DARPA is that the secret of DARPA grants is getting the right acronyms. So our acronym for this is that what we want are systems that are messy, that are model building, exploratory, social learning systems. And again, those of you who have children at home will appreciate the relevance of this acronym. So there's 3 elements that we think are crucial for this process. One of them is the model building, that children are building abstract models, particularly abstract causal models of the sort that people like Judea Pearl have talked about from statistical evidence. And in my work over the last 15 years, we've shown that children are amazingly good at doing this. Again, it's computationally quite challenging to see how you can do this in a general way. The second thing is that children are learning through imitation. They're learning from other people. And again, there's 20 or 30 years of work showing just how good and sophisticated children are at doing this. And people like Anke Dragan at Berkeley are trying to figure out how we could use that kind of imitation learning to do things like train robots. But the third thing is this idea of active exploratory learning. And I'm just going to very briefly talk about a couple of projects that we're doing in that regard. And that active learning through exploration and play is particularly relevant because children actually seem to do more of that kind of exploratory learning than anybody else that we know about. And I've actually argued that the very fact of childhood, this very extended period that looks kind of useless, where the kids are not being productive and they're running around and they're crazy and they're bouncing off the walls and they're making a mess, again, something that will be relevant to those with children at home, you could actually think of as a way of resolving explore-exploit trade-offs. So one of the things that we know from computer science and neuroscience is that there's always this intrinsic trade-off between being able to act effectively and swiftly and efficiently on the one hand, and being able to explore the space of possibilities on the other hand. And what I've been arguing is that children are actually designed to be that kind of explorers. You could think of it as being that they're released from the pressures of exploitation, AKA they're taken care of by us, in order to be able to have this period of exploration. And from that perspective, many things that would seem like bugs, if you just wanted a system that could act as efficiently as possible, are actually features if you want a system that's going to explore the space of possibilities. So things like having a system that's got a lot of noisiness, a lot of variability, a lot of randomness, a system that's very willing to take risks, even what look like irrational risks, a system that's impulsive, a system that spends all its time playing instead of actually doing anything useful or productive, and a system that's insatiably curious, even if it gets it into trouble. Again, those of you who've been looking at your 3-year-olds will recognize all of this, even though that might seem like a terrible design from the perspective of a system that's going to go out and do things. It's a very good design from the perspective of a system that's going to explore possibility. So what we've been thinking about is, could we design AIs that have some of these kinds of features? And in fact, what we've discovered empirically, we and others, is that when you look empirically at children, we have a paper coming out, I hope soon, in Nature Human Behavior showing this, that children characteristically and systematically are actually better than adults at this kind of exploration, even though they're almost always worse than adults at almost all other kinds of tasks. So what we've been doing is collaborating with 2 groups at Google, with people at Google DeepMind and also people at Google Brain, trying to take this idea of curiosity-driven exploration and see how both AIs and children compare in this regard. And this is work with Deepak and Pulkit and Alyosha and Trevor. And the person who's the center of this is Eliza Koso, my graduate student, but we're also working with Jasmine Collins and David Chan, who of course are the students who are doing all the work on this. And what we've done is taken this environment, this deep lab environment that the DeepMind people have designed, which is an exploratory maze that you can design that has different kinds of reinforcement possibilities and different kinds of goals. And we've set up an interface so that we can actually track how both children and curiosity-based AIs are exploring these mazes. And what we can do is set up different regimens, things like dense rewards versus sparse rewards, things like completely free exploration versus goal-directed exploration. Then we can track what the behavior of the children are, and we can compare it systematically to the behavior of a variety of different kinds of AI mechanisms. So one thing that we're doing is taking a curiosity-based AI, and I won't go into the details of this, just give you an idea, and in these various conditions with different kinds of rewards, see how it compares to the children. But another thing that we're doing is actually in collaboration with Jess Hamrick at Google. We're looking at how the children are, what kinds of traps the AI systems fall into, and whether children are falling into similar traps or escaping from those traps. So the general idea is that we can put children in literally the same environment as the AI, and then we can see how the child's exploration and curiosity compares to that of various kinds of AI systems and how effective those are in the long run. The second project that we're doing, this is with Corey Lynch and Igor Mordach and Pierre Sermonet at Google Brain, is we're taking an idea that came from them independently, which is this idea that you might be able to learn from play. And essentially what Corey did was look at, they were using imitation learning to try and train robots. And And what they discovered was that if you actually train the robots by just showing them the kinds of behaviors that you want them to do, even though they learn those behaviors, they're not very robust. They can't generalize very well to other cases. Whereas if you show them something that looks more like play, that looks more like just someone messing around with a bunch of objects on a desk, you cover much more of the space. So you're actually doing that exploration that is part of the explore-exploit trade-off. And as a result, the machine that you're training is more robust and better at generalizing. So what we're doing is setting up, again, a virtual environment, this time a kind of child's play environment with a bunch of toys that you can play with, that you can do various kinds of intuitive physics on, you can make them stack, you can drop them. And then once we get our IRB approval, which should be soon, we will be having both children and robots in this virtual environment. And what we can do is take actual play by real children, which I can tell you, we already have some evidence covers a much wider range of dimensions than even a creative Google engineer trying to play with something. And then see what happens if we use that kind of play to, train the robots. Ken, my timer doesn't seem to be working. How much time do I have left?
You have a minute and about a minute.
Okay, great.
For 12 minutes, and then we have 3 minutes for Q&A.
Okay, good. So those are the projects that we're working on, and we want to take this idea of the child as explorer and use it for AI. But in the minute that's left to me, I just want to raise another set of theoretical ideas that I've been working on that we don't have a good way of implementing yet, and they come out of my 2016 book, The Gardener and the Carpenter. And they're about the fact that this whole idea of, let me say the picture, by the way, which I love. This is the Child Study Center, which is at Berkeley, around the corner. You can donate to it. In 1925. So the Child Study Center has been around for 100 years. It was one of the very first examples of a preschool for children. And this is actually footage from the 1920s of children playing in the Child Study Center. And the point here is that the reason why children are capable of doing, this is a good illustration of the kind of beautiful spontaneous exploration that children do, but the reason why they can do it is because of her, because there are caregivers around who are both, keeping them alive and giving them lemonade and peanut butter sandwiches, but those caregivers are doing something else. And what they're doing is really remarkable. The caregivers are allowing each generation to autonomously discover new values for themselves, both discover things about the world and develop new values, develop new, as it were, objective functions. And yet somehow in the course of doing that, the caregivers also ensure that those new values of each generation are positive values, are all in general good values. And my friend Stuart will be talking, I'm sure, about this value alignment problem in AI. On the one hand, we want AIs to be autonomous and to develop their own values. That's what it would take to be genuinely intelligent. On the other hand, we're terrified that they're going to end up with values that are negative, that are not ours. And we could have the sort of Stepford Wives solution, which is to just get them to find out exactly what our values are and then implement them. But I think the childcare solution, which is you have these creatures, you give them a measure of autonomy, and yet you shape their values and objectives so that they can be autonomous and yet be good at the same time. I think that might be a better cue, a better indicator of how we could create a new generation of intelligences, which is actually something that we've been doing with our children as long as we've been human. So with those beautiful pictures, let me stop and see if anyone has any questions.
That's great. Thank you so much, Alison. Love that video. I've never seen it before.
Isn't it gorgeous? Yeah.
And of course, the alternative is something like Lord of the Flies, right? If we just let we let these agents run free without any supervision.
And the point of the title of my book, The Gardener and the Carpenter, is one picture you could have of how you could create agents that can be intelligent is that you go in and you shape exactly what they're like to end up with the values that you want. And that's not what human beings do with their children. Instead, what we do is have, like gardeners, we're creating this rich environment, and this is a beautiful example. And then within that rich, controlled environment, the the agents can actually do exploration and including making up new values.
It's really interesting that you mentioned garden in this sense, because Froebel had this idea of the kindergarten.
Exactly.
Which is another garden. Okay, Shankar, you have the privilege of asking a question if you'd like. We also, anyone can raise their hand on the interface, and we'll try to get to you. Alison, while we're waiting for this, I love this interface. Are these, did I see it correctly that there's these little almost Play-Doh buttons that the kids push? Okay, and they electrically react, and then they can steer around a maze?
Yeah, exactly. And this is all Eliza's brilliant doing. You can see, so she actually used like an Arduino with these Play-Doh buttons so that the children can interface. And the very first thing we wanted to know is, can children even do this, right? And what we discovered, the problem was not getting the children to do it. The problem was getting the children to stop. So you essentially put a 4-year-old in this environment and you say, look, see, this button will make it move like this. And then the problem is that 20 minutes later, you have to say, okay, now we're going to stop and go and play another game. So it is interesting that the children, in this what looks like a somewhat unnatural environment, get the idea of navigating just like that. And then they are so exploratory that even if, our basic assumption is we don't even have a goal, we just say, you can play and figure out how this works. And when we do that with minimal instruction, the children are covering most of the maze.
Amazing. Great. Okay, thank you so much. I'm going to pass over Pieter Abbeel is up next, and Alison, if you unshare your screen, then Pieter will jump in. Thank you again.
That's what I'm trying to do, although I
want to say I really appreciate the way you offer some philosophy and thinking about where you're going next. I think that's really important that we try and do that in these talks, because this is why we're here, is to sort of talk not only about what we've done, but new directions that we're excited about. Okay, with that, Pieter.
Okay, there we go. Good.
Thank you, Alison. Pieter, you're up.
All right, thank you, Ken. So let's see. What I thought we'd do is check in what's new since fall retreat, which was in December. One of the big new things that Bair Commons has started, and so I'm very excited about a project we started with Sergio Guadrama from Google on realistic RL benchmarks where reward specification is challenging. And so what we're looking at here is Minecraft and trying to see if, even though the reward is not that obvious, there is no single score there, if somehow meaningful learning can emerge in this kind of environment, maybe based on initially looking at some human play data and then working from there. We just got started on this, so no results to report just yet, but just wanted to share my excitement about this project. Then also, if you want to kind of keep up at your own pace, here's a link, a bit.ly link to the slides and the papers that I'll be covering. So that'll always be at the bottom left of my slide if you want to download that as we're going through this. So what's happened since the fall retreat? A few things. We looked at how to do adaptive online planning, where if the dynamics of the environment changes, how to dynamically choose between continuing to use a learned policy versus resorting back to model predictive control, which of course is more compute intense. And so the optimization objective here is kind of minimizing the amount of compute needed, where MPC is more expensive than using a learned policy while still having great performance. We also looked at new representations for intrinsic motivation. There's been quite a bit of work on the direction of variational intrinsic control lately, which looks at mutual information between state and sequence of actions and the resulting state later on. We've been looking at information theoretic approaches to estimating that mutual information more precisely than was available before. In Avid, we looked at leveraging CycleGAN, which you probably remember from Alyosha's presentations from a couple of years ago. And we're looking at CycleGAN where we try to automatically translate videos of humans into videos of robots. We have unpaired video sequences of humans and robots. And we learn a translation between them, so that when we get a new demonstration by human, we can get a robot video, and the robot can try to imitate its own video of achieving the same task. In the fourth paper here, we looked at how to get a latent representation in pixel CNN style models. Pixel CNN has not a natural latent vector. We investigated how Fisher scoring actually can give us a latent representation where interpolations become meaningful. Then, together with our host here, Ken Goldberg, we looked at hierarchical variational learning of control programs. So how can we learn through neural net architectures, how can we learn to mimic what's happening in traditional computer programs, and maybe from there, automate some programming in the future. We also looked at boosting reinforcement learning in settings with sparse rewards by doing contrastive learning to learn latent representations that capture proximity in an environment, which then in turn can be used for reward shaping, which can speed up the learning. Another very different problem we looked at is, imagine you're a company and you trained your, I don't know, self-driving car policy, and now your neural net is controlling your car. But now let's say somebody drives that car, collects the data, and can just use supervised learning to clone your policy. Then they've extracted all the important things from your policy, and maybe they can compete with you. Can we design policies in a way that it's harder for behavioral cloning to succeed? We need to give it a little bit of extra leverage here, so we allow it to learn an ensemble of policies such that if you directly behaviorally clone the ensemble into a single policy, you actually get pretty poor behavior. Then we actually looked at some autonomous driving with a small robot car in the wild, and specifically investigated how we can go beyond just looking at geometry. So traditionally, this kind of navigation is done purely by looking at geometry, but then you would see a point cloud that's pretty dense and that you wouldn't want to go through with all the grass sticking out. How can you do more semantically meaningful navigation in these environments? Another thing we looked at is cross entropy is kind of a baseline method that's very effective at optimization, very popular, but it also has a pretty big downside in that it tends to find a single solution. So it tries to fit a Gaussian to the region of the minimum of your objective. And so what we looked at is, with modern generative models, can we fit richer distributions rather than just a Gaussian through autoregressive models that allow us to find multiple local optima of a function we're trying to optimize. Here are a few stylistic examples of famous functions that have multiple local optima where it works pretty well, but we also looked at more real things like circuit design. We looked at generalizing hindsight experience replay. Hindsight experience replay essentially relabels trajectories with new goals after the fact, such that all of a sudden that trajectory achieved high reward against that new goal. So you can get solutions in sparse reward settings by after the fact relabeling the trajectories. We looked at generalizing this to more full reward functions rather than just goal-based rewards. Then another thing probably many of you have seen is the work on SPTM and SORB, search on the replay buffer, which is ways to build graphs over the state space to do planning in graphs that were initially only have visual access to the space. One of the limitations of these methods, even though very effective for navigation, is that they are for a fixed environment. And so what we looked at here is, can we do the same thing where we can now condition on a few observations of the environment to generalize what the entire environment might be like and build a graph for this new environment that's not an environment exactly seen at training time. We also looked at transfer for agents of different morphologies. So if a point mask can learn to navigate the maze, that skill should be reusable by an robot to learn to navigate that same maze more quickly. Then we continued what I talked about the most in Fall Retreat, which is a robot learning to fold laundry, to manipulate deformable objects, and we brought in a bit longer term planning. The key idea here is that we use contrastive estimation to learn a latent space model over which we can do planning over longer horizons than was otherwise possible, allowing it to do much more reliable cloth manipulation and rope manipulation. And then the last paper I wanted to quickly highlight is another, in some sense, extension on the sparse, on the graph models. What we look at here is that SPTM and SORB have the challenge that they are very dense, so it can be expensive to plan in. So we looked at how to sparsify. And we also looked at how, if there are spurious edges in the graph, how to dynamically adjust them with recent experience from the agent. So that's a quick overview of the things we've been working on. Then what I want to do in the second half here is dive into one specific paper, contrastive unsupervised representations for reinforcement learning with Misha Laskin and Arvind Srinivas. This paper will probably go on archive later this week, maybe the week after. So the question we're looking at is, if we do reinforcement learning, you can either do it from pixels or from state in, let's say, a Majoko DeepMind control suite environment. Here we see some state-of-the-art learning. In blue, we see the learning curve when it's done from state. In green, we see the learning curve when it's done from pixels. But you might argue that in principle, the pixels have most of the time the same information as the state. So why should the learning be slower from pixels? In principle, maybe this gap can be bridged with more efficient methods. And that's specifically what we've been trying to look at. Can we bridge the gap and make learning from pixels as efficient as learning directly with state access? So starting point is a lot of progress in contrastive learning in computer vision. There was the contrastive predictive coding V2 paper from DeepMind that came out last year that showed consistent outperforming of a combination of unsupervised and supervised learning compared to just supervised learning for the first time in vision. And then on the right is the plot from one of Jeff Hinton's recent papers, SimClear, showing the effectiveness of contrastive learning for image recognition. If you look under the hood, this is from the SimClear paper. You take an image and you make 2 augmentations of that image. And then those augmentations you turn into embeddings. And if the embeddings are coming from augmentations of the same image, then the embedding should be close in cosine distance. If they're coming from different images, then they should be far in cosine distance. And it turns out that just that very simple objective allows to internalize a lot of the invariance that we think about as important in computer vision and gets really good performance. So as we look at this in the context of RL, do the very similar thing here. We have an actor critic model, augmented observations, unsupervised learning. We look at where the image lights up. We see it lights up, the features light up around the robot, which is a good sign. The unsupervised learning is picking up on the important things. We couldn't use a cosine distance. I mean, we tried, it didn't really work, but the bilinear contrastive objective worked a lot better for us, as you can see here in red. And then the other thing that was very important, which Kai-Ming Ho proposed a little while ago in MoCo, is to use a momentum encoder for our encodings. Without it, it again doesn't work nearly as well with momentum encoder in red. All right, so the main results here in gray is the learning curves for state-based learning. In red is for image-based learning with the contrastive unsupervised learning as part of it. And we see that in many of the environments, the red curve is almost as good or even as good as the gray curve, showing that we've largely bridged the gap between state-based learning and image-based learning for these DeepMind control suite environments. One caveat, not all of them. There's a couple where that's not true yet. Before we get to that, let me show this plot here, which shows that also against existing model-based methods like Planet, it outperforms those methods. Here is a more extensive table benchmarking against the state-of-the-art image-based learning for a DeepMind control suite, showing that curl consistently outperforms all of them in these environments. Same as I should throw in Atari. We did the same experience for Atari. We did it on 9 games so far. It almost consistently outperforms past method, including Simple, which is a model-based method, and Rainbow. But of course, curl is an augmentation on top of Rainbow, so we expect it to outperform Rainbow quite consistently.
Rainbow is an ensemble?
Say it again?
It's ensemble method, Rainbow?
Rainbow brings together pretty much all the machinery that DeepMind has built for learning the Atari environments in one method.
Right, so that's the ensemble.
So it's not an ensemble method per se, but it brings together all the machinery they have brought to bear in other papers in the past.
Okay. Pieter, I'm sorry to interrupt, but because this is really fascinating. I can't wait to see this paper. We are a little low on time, so we have probably another minute for you.
Oh, thank you, Ken. Let's see. In the 1 minute we have, what I want to do is maybe look at where it doesn't work yet and give some hints at that. So skip over this one. So here are the environments where it doesn't work as well yet as learning from state. And so the experiment we ran is to take data and just run supervised learning on these environments from image to state. And we saw that there's a very strong correlation between environments where you are not able to regress the state from images and where RL from images cannot match learning from state, which is, of course, what you'd expect, but we checked that. And so it turns out that in some of these environments, the state doesn't seem available in terms of information-wise being available. Even in a stack of frames, we use a stack of 4 frames. So let me wrap it up here. Thank you.
Super. Thank you, Pieter. Really interesting. Okay, Alison, I'll give you the option of asking a question. If not, I have one. And also anyone else, if you please raise your hand. We're up to 182 people online right now. So it's a big group. Seems to be pretty manageable.
Pieter, I could ask a general question. It seems as if there's been a move from having this kind of dense reward reinforcement learning as the core example of what we could do with AI learning to more and more unsupervised attempts at unsupervised methods. What do you sense the future is going to be between the relationship between those two things? It looks as if these are some examples of how to combine model-based unsupervised and sort of densely supervised RL.
Absolutely. So there's really two places to get more information from, I would say, that are seeing a pretty big push, and I think there's a lot more to be done. The one I highlighted here is unsupervised learning on the image space or the stack of frames to essentially get close to state-based learning, even though all you get is pixels. The other one is closer to maybe what you're alluding to, is the curiosity line of work, to have intrinsic motivation to try new things. And I don't have any highlights of that here, but actually, yeah, Deepak and Alyosha have pushed that pretty far in recent years at Berkeley. And of course, many others have pushed in the same direction. And I think it remains many open problems there to take that to the next level, especially when considering longer horizons over which problems need to be solved.
Great.
Fantastic. Thank you, Pieter. Okay, so we have David Wagner coming up next, and then we have a break, about a 15-minute break, which you might trim a little bit. David, are you online? You could unmute. Oh, great. Perfect. So David, if you just share your screen. Thank you again, Pieter. David, you have the floor.
Great, thanks. So I'm going to be talking about our group's work on looking at how to defend against adversarial examples. So neural networks have come a huge way in enabling us to do a lot of powerful things, but unfortunately, we're way behind on defending against adversarial examples. And if you're not familiar with adversarial examples, basically they're a phenomenon where making a very slight change to the input, for instance, to an input image, can completely mess up the neural network's prediction if that change is chosen by an adversary. So this is particularly relevant where we think there might be some kind of attacker who's trying to attack our system. And I wanted to show you some of the work we're doing, especially inspired by perception for autonomous vehicles and trying to make that more robust. And here's my one slide. If you don't pay attention to the rest of this talk, here's the one slide of progress since we last spoke at the last retreat. First, I want to show you about results on using generative models, and using those, we've been able to get a state-of-the-art robustness against adversarial examples for SVHN street number data set. and a large data set of traffic road signs. Second, we've made some improvements to adversarial training, making adversarial training more effective. Adversarial training is perhaps one of the leading defenses right now, and we have improvements using curriculum learning. And you'll notice this is not, I don't believe that this is state-of-the-art version of adversarial training for kind of a funny reason, which is that concurrently another group recently released results that were better than ours. And it turns out they're using very similar methods. So I think the curriculum learning, there's something interesting there. And then third, I'll tell you briefly about work we've been doing ensuring robustness against sticker attacks, where an attacker places a small sticker on an object, and we'd like that to not mess up the classification process. And we have state-of-the-art certified robustness results on small data sets like MNIST and CFAR, as well as another technique that scales up to ImageNet. Okay, so let me walk through each of those for you. Let's start with looking at generative models. Now, in previous work, there's a groundbreaking paper from Lucas Schott et al. Proposing how to use generative models to achieve better robustness against adversarial examples. And here's how they use generative models for classification. They take an autoencoder, think a VAE, a variational autoencoder. And the way variational autoencoders work is they take an input image, like that 0 shown on the left, and they map it to a latent vector. And then there's a decoder that maps it back to a reconstructed image, an attempt to reconstruct the original image from this low-dimensional latent vector. And you'll notice the reconstruction is pretty good. We train a separate VAE for each class. So when you use the VAE for class 0 on a 0 image, you get a very good reconstruction. Of course, if you take the VAE that's trained on images of class 9 and try to apply that to an image of a 0, then you get a very bad reconstruction. It's trying to turn that into the closest looking 9 it can, and that's not very close to the original image. So this gives you a way for classification, which is basically for each class, we get some class conditional likelihood, and we see which class has the highest likelihood. Or in other words, which of these reconstructed images is most similar to the original. Well, it turns out that doesn't give you robustness, but if you throw away those encoders, the problem is encoders map from a high dimensional image to a low dimensional latent vector space, and that can be exploited by adversarial attacks. But the idea of the Schott paper is that they throw away the encoder and they use optimization methods to find the best latent vector that gives you the best reconstruction. And that turns out gives substantial improvements on robustness. So they showed that for the MNIST, this is better than anything else. But unfortunately, their method just didn't scale up to anything beyond MNIST. So what we've been doing is we've been looking at applying this to data sets for perception and autonomous vehicles. We've been looking at classifying road signs, for instance, and trying to scale up their method to work with more complex data sets. Okay, and so we've found several improvements that improve the quality of the autoencoder and also improve their performance on out-of-distribution samples, basically that address two of the major shortcomings that were limiting this from scaling and that bring this approach a little bit further towards more complex data sets. So I'll show you our evaluation on the SVHN. That's a street number sign data set that's similar in style to MNIST, but is more challenging for networks. And what you can take away from this, this picture here is an unprotected CNN has good accuracy, but very poor robustness. We want higher robustness numbers. Using the Schott method gives better robustness, but very, very poor accuracy. You just pay too much in accuracy. Adversarial training, the other standard approach, is better, but we can do better than either of those. We get substantially more robustness and also recover closer to the accuracy of an unprotected convolutional network. We've also evaluated on a data set, an aggregate data set where we combine the 3 largest data sets for road signs, where we find that here we can, again, improve over all the previous schemes. So we have a state-of-the-art scheme here that has better robustness and better accuracy than other methods for defending against adversarial examples. But here the improvement is more modest, and there's still a substantial gap in accuracy on clean images compared to an unprotected CNN. So what you pay for robustness, you still pay quite a fair bit in loss of accuracy when you're not under attack. So there's still quite a ways to go. But I think it's interesting progress. Here we have the state-of-the-art defense against adversarial examples for these 2 particular data sets. So I think generative models are an interesting direction. Let me also talk about a little other work we're doing. We've been working on improving adversarial training. Adversarial training defends against adversarial examples the same way your immune system does. We expose the network, we train it on these hard cases, we synthetically generate adversarial examples and we train on them. Adversarial training helps but has some limits, and the idea that we're looking at using curriculum learning. So train on easier examples first before you go to the hard ones. Train on adversarial examples that are easier to learn from than before you go to the full strength ones. And so we do that by using early stopping when generating adversarial examples. Don't generate the most powerful adversarial examples, generate ones that are just good enough to fool the current neural network. So kind of minimum strength rather than maximum strength. And here's how well this works. The black lines are previous methods and the blue is our method. And what you want, what this is showing is the accuracy, how the accuracy degrades if the attacker starts modifying the image. So all the way on the left is the accuracy if there's no modifications to the image, and then as we increase the amount of modification that an attacker is allowed to make to the image, what does that do to accuracy? So current methods for MNIST are very good up to a certain certain amount of modification. You can see that dotted line, but then drops off very sharply once the amount of modification goes above about 0.3, L infinity norm of about 0.3. And if you try to train adversarial training on previous methods, adversarial training on harder adversarial examples, it just gets stuck and can't learn and is stuck in a horrible local minima. And so curriculum learning gives you the blue curve. So there's substantial improvements against larger perturbations. Here's how things look on CFAR 10. If you use a convolutional network and you try to train this against fairly large modifications to the image, standard adversarial training just dies. It gets stuck. It can't learn anything. It's stuck at that 10% accuracy black line on the bottom. If you use curriculum learning, you do substantially better. And it turns out that if you use network models with a higher capacity, like a large ResNet, then actually adversarial training works better, and our method also works better. So you get improvements over the current state of the art. Okay, let me also mention something about sticker attacks. We're looking at sticker attacks because we think they're physically realizable. An attacker might plausibly be able to place a small sticker on a road sign, on a lane marker, on something like that to try to mess up your car. Might be a relatively feasible attack. And right now, all of our methods are vulnerable. A small sticker could change the classification of an object. And the approach we're looking at is looking at a defense where we try obscuring different portions of the image, and if that changes the classification, then that's something suspicious is going on. And in this way, we can get certified accuracy, where we get guarantees that no sticker of a certain size would change the classification. The previous best method, for instance, on CFAR 10, really hurt accuracy in the absence of attack, and it obtained only modest certified accuracy. And we're able to recoup most of the clean accuracy, gain clean accuracy that's much closer to what unprotected networks are, and still for a substantial fraction, the majority of images guarantee that they're safe against a sticker attack.
David, I just don't want to rush you, but it's just about a minute left.
Great, perfect, thank you. We tried some things that so far we couldn't make work. So we talk a lot about what works. I thought I would just briefly mention things that we just couldn't make work. We tried using part-based classification to decompose a scene or an object into parts and robustly classify each part, and just didn't seem to work. We tried using k-nearest neighbors, didn't seem to give us better robustness. We tried really hard. And what we're currently working on is inspired by conversations from some of you at the previous retreat and some of the industry folks. We're now trying to move beyond object classification. A lot of the folks in the adversarial community, the security community, look at robustness for object classification, and we want to move beyond that to object detection, locating objects in an image when we're not sure where they are. And one of the first things we're looking at there, one of the first applications we're looking at is robust lane detection. And this is inspired by several recent works that show that they can attack lane detection in Tesla cars and in theoretical cars and in other settings to cause a car to drive out of the lane. All right, so I'll stop there. Thank you very much for your attention.
Thank you, David. Terrific. Okay, Pieter, would you like to ask a question or two?
Yeah, David, really nice presentation. One thing I'm curious about is in the second part of the presentation, it looked like you had perturbations of level 24 out of 255. I'm assuming that's like pixel values, right? 0 to 255. Can you give a sense of how visible those perturbations are to human eye? Because it seems like at that level already, it still causes a lot of trouble. Do humans have any trouble with those kind of images, or is it still imperceptible?
That's still a pretty small change. I sometimes have trouble, but just because I have trouble with CFAR 10 images even without any modification. But this is a far way away from the level of robustness that humans have, I think. So we got a long way to go if we want to match humans.
If I can ask a follow-up question for the third part, it seems like there's a bit of a performance hit when making things robust, right? Because I think the best CFAR 10 performance is 99% at this point, roughly. And it was 88% for the clean data set once making it robust. What's your intuition? Like, why does robustness cost us here?
Yeah, a lot of the things we're looking at have a hit, and there's some trade-off there. I think that the hit is partly due to poor engineering on our part. We're working with a base model that's not the full strength, latest ResNet, et cetera. So our base model that we started from before we added protection was only at 90% accuracy. So
very small
put in the engineering, we might see better there. But still, this is definitely where we're at today, is this trade-off where you pay a cost and inaccuracy when you're not under attack, and that's probably not satisfactory. So I think that the techniques that I'm showing you are not something that I would go race out to deploy today. It seems like we've still got ways to go.
Got it. Thank you, David.
Professor Wagner, we have a question from Ruslan Lagashkin. Can we map decision boundaries and use distance from decision boundaries as an evidence of adversarial attack?
Yeah, that's an interesting direction. I've read a few papers that are looking at this kind of direction. One of the challenges with that is that on a standard model, our intuition is that examples should be far from the decision boundary usually, but that's wrong. From most directions, you're a long way away, but there's some rare dimension. You're in such a high dimensional space. There's some rare dimension where you're close to the decision boundary. And that's kind of true for both normal examples and adversarial examples, attacks. So just straight off the bat, it's not so trivial to distinguish attacks from benign based on distance to the decision boundary, because in a high dimensional space, in some sense, everything's close to the decision boundary. So there's definitely work on this direction. There's trying to do some more sophisticated things, and I'm not sure whether that's going to pan out or not. It's kind of an interesting direction, but it's not straightforward.
Okay, thank you, David. Thank you to all the speakers, and I know there may be some more questions. You can direct immediate special questions, by the way, to the speakers via email, what I'd like to do now is take a break. We are a few minutes behind, almost 10 minutes behind. So what I'd like to say is we'll shorten our break by 5 minutes, and that will bring us back here at 11:45 for the remaining talks. We have Ren, Mike Jordan, Dan Klein, and Stuart Russell, and then we have a lunch break before the office hours, 1:30 to 2. So I realize that's not a huge amount of time, but if everyone takes a few minutes to get a cup of coffee and chill out for a few minutes, we'll be back at 11:45 with Ren. And Ren, if you wouldn't mind, maybe you could share your screen in the meantime. Or add a note that you'll start at 11:45. Please start recording.
All right, thanks, folks. Thanks, Ken. Okay, so it's my pleasure to introduce today 3 of my grad students who are going to be doing the speaking: Ben Mildenhall, Pratul Srinivasan, and Matt Tansik. I'll just say something for a minute to kick it off. So they're going to present a new work, hot off the press, that I think represents a breakthrough in view synthesis. They published it on Archive 3 days ago, and it's already been trending on Hacker News, GitHub, and YouTube. So view synthesis is a super hard problem that researchers have been struggling with since the 90s. It's also known as unstructured light field rendering, for example, in computer graphics. So the problem is, here, I have a little prop here. Okay, so here you go. So here's an object. Okay, so the problem is to take just a handful of photos of an object like this, and then interpolate new images of this object from any viewpoint from just those handful of photos. Easier said than done. For example, consider that if you wanted to Nyquist sample that problem for typical scenes that you'll see today in the results, you would need millions of photos. One of the strengths of the way that Ben, Pratul, and Matt's work has unfolded is that they've distilled this view synthesis problem into a minimal, almost pure formulation that they'll share with you. And it produces the best results I've ever seen. Ben and I have been collaborating with this project with John Barron at Google under the Bair Commons program that you've heard about. Ravi Ramamurthy from UCSD is our co-author. With that, take it away, fellas.
Thanks, Ren. I think Matt's setting up the screen share now. Okay, yeah, so I'm Ben, and I'm going to introduce this latest project, which, as Ren said, was just posted on Archive a couple days ago. And yeah, this is a project we have been doing under the Bair Commons umbrella with John Barron on the Google side. So yeah, as Ren was saying, view synthesis is a really classic problem in graphics and vision. It's been worked on for decades. And the basic premise is that you want to take a sparse set of views of a scene as input and then use them to smoothly interpolate any new view of the same scene. So if we consider some smooth camera path in 3D observing these flowers, on the left we're showing the nearest view you would find in the input data set. And on the right we're showing, by comparison, newly rendered views along that smooth path. And here the left side should look really jumpy and have big gaps between the views, and the right-hand video should look completely smooth. And we're not sure how well everyone's going to see these videos over Zoom. So if the right-hand video looks choppy, please take a look at the online videos we're going to link to at the end of the talk for better comparisons locally. And we want to emphasize again that this problem is really hard, and people have only recently just started making reasonable results for really complicated real-world scenes like this one. And local light field fusion was a different project we presented at SIGGRAPH last year. It was a pretty heavyweight deep learning pipeline that was trained on tons of synthetic data to do this task. And despite using a much conceptually simpler algorithm in this new approach, we're still able to exceed the performance of LLFF and get closer to our target of photorealistic output renderings. And if we look at a more direct comparison to a conceptually similar approach to a NERF, such as scene representation networks, we can clearly see we've made an enormous jump in output quality, both in terms of overall sharpness and in consistency as the camera is moving through the scene. And the underlying nature of this conceptually simple approach is that we're directly encoding a function that represents the scene in the weights of a really simple, standard, fully connected, non-convolutional MLP network. And this is similar to SRN and also to other recent work such as DeepSDF. But we've made a lot of changes that help us achieve top quality view synthesis results with this exact type of representation. Now, summing up what we want to present in this talk, We're presenting state-of-the-art results on this classic and difficult problem, and we're going to use an approach that's much simpler than recent methods that are targeting view synthesis specifically. And our method specifically is encoding a continuous 5D volumetric representation of the scene inside a neural network, and then directly optimizing that network for only a single scene using gradient descent. And we're also going to show there's one key trick we found that greatly improves the ability of a network to perform this specific task. So first, to provide some context for our simple network-based scene representation, we'll quickly review what some standard representations might be for recovering a scene using only images as input. So again, the task here is to do some kind of optimization or learning-based procedure that's going to transform these 2D input images into a representation that lets us render new views of the same scene. And it turns out the most standard graphics representation, that's triangle meshes, is not really good for this. Triangle meshes don't interact well with gradient-based optimization because you need a pretty good initialization to even get something to converge at all. In contrast, representations that are dense in space, like voxel grids, are much better behaved. The rendering models are easier to differentiate, and they can be incorporated directly into gradient-based optimization. However, if you want to start driving up the resolution of the dense grid to produce higher quality outputs, you have to pay a really large storage cost. You could be looking at up to gigabytes to store a single scene like this. So instead of a discretely sampled volume representation, we're just going to create a function that directly maps from locations and ray directions, 5-dimensional space, to an output that's a color and a volume density at each point in the scene.
Yeah, so this leads us to our presentation, which we call neural radiance fields, because they encode the scene in the weights of a deep network, and they represent the scene as a radiance field, which here means a continuous field of particles that block and emit view-dependent light. So all we do is represent any arbitrary scene as a simple, fully connected network. In this diagram, it's f sub omega. And this network just has 12 layers of 256 channels each. The network takes in a continuous 5D coordinate, which consists of a 3D location xyz and a 2D viewing direction theta phi. And then the network outputs the volume density sigma of the particles at that location and an RGB value, which represents the radiance emitted by a particle at that input location and along the input direction. So to render an image from this representation, we just need to estimate how much light of each color makes it out of the volume along each camera array. And so here's an example of 2 images viewing this Lego bulldozer. And so for our actual results, we actually use many more images, but here we're just going to show 2 for visualization. And to render each of these views, we need to query the network at a bunch of discrete points along each ray, and that's shown in black here on the left. And the network outputs the corresponding view-dependent colors and volume densities, and we're visualizing that on the right. And then we use compositing techniques from traditional graphics volume rendering to collapse them into a single color for each ray. And this volume rendering process is trivially differentiable with respect to the network's outputs. So we can optimize the network parameters by just using stochastic gradient descent to minimize the error of rendering all the input images. And note that this only involves minimizing the loss from rendering just the input images and requires no external data for training. So here's what happens if you implement what we just described and optimize the MLP using about 25 images of the scene of a large plant. And it looks okay, but it's still really blurry. And so our actual results actually contain really sharp details like this. So we're going to tell you about a trick that we found that helps the network encode much crispier content in the scenes. And interestingly, this problem where the network outputs a blurred representation is actually representative of a more general challenge in getting deep networks to represent higher frequency functions. So to illustrate this issue, let's quickly drop down to a simple toy problem where we want to optimize a deep ReLU network to memorize a 2D image. And so the input to the network is a 2D pixel coordinate xy, and the output is going to be the RGB color of the corresponding pixel. And we'd think that this would be super easy, right? But actually training a standard fully connected deep network to memorize the image in this way can't even converge to a sharp representation. And this is really surprising, especially considering that the network has 8 times as many parameters than the image even has pixels. And so we found a pretty simple way to enable the network to represent high frequency functions by just mapping each of the input coordinates to a higher dimensional space by encoding them with a set of sinusoids with exponentially increasing frequency. And so we apply this pretty simple transformation to each one of the coordinates before passing them as input to the network. And it's interesting to note that this is actually the same mapping that's used in the transformer architecture literature, but they use it for a really completely different purpose, where they want to encode the relative position of words in a sentence. So now let's look at the results of this toy task if we use the embedding before passing the input 2D pixel coordinates to the network. And now the network is able to easily, accurately memorize the image. And if we apply this exact same mapping to our input 5D coordinates of location and direction for our real problem, it results in a similar improvement. And this is cool even though our task is different than function memorization, right? Because it indirectly supervises MLP through differentiable volume rendering.
So now let's take a look at some results. Each of these scenes uses between 20 to 50 input images. I think it's worth reiterating that the model is only about 5 megabytes, which is really quite small, especially when you consider that the inputs during training are much larger. As you can see, we are able to reconstruct a variety of different complex scenes, both indoors and outdoors, and small and large scenes. We're even able to reconstruct foliage, which is traditionally difficult due to the number of occlusions in the scene. And finally, we show some 360 results using this method. Here we show some examples on a synthetic data set we created. Each model uses 100 input views. In some of these examples, you can see why the view dependence is necessary. For example, if you look at the bottom row at the ship, you'll notice that the water changes reflection depending on what angle the camera is. Here we show our model compared to the latest computing work. On the left, we see that scene representation networks, which also uses an MLP, is not consistent. Local light field fusion is able to capture more details, but it is also not consistent. And finally, neural volumes, which uses a discrete voxel representation, is able to produce more consistent results, but it can't resolve to the same level of detail. You can see this in the ship's rigging. So in summary, we show that it's possible to encode a detailed scene into a neural network. We were able to produce state-of-the-art results in view synthesis using a surprisingly simple approach. We encode a 5D volumetric scene representation with a neural network that is optimized with gradient descent. Finally, we show that passing positional encodings into the network helps recover high frequencies. We think there's a lot of exciting follow-ups to this work. For example, we found that NERF is able to encode pretty convincing view-dependent effects. This is a visualization of the view dependence. We think this could be useful in a number of applications, such as recovering scene materials or relighting the scene. Here's another scene where we visualize the view dependence. Notice the specularity is changing on the back of the stove or on the back wall. If we visualize where the rate terminates, we can generate a depth map. We were surprised and excited by how sharp the details are, particularly in the flower of the scene. Here's another example of the predicted geometry. Note that our method's able to pick up small details like the pine needles or the holes in the ornament. There are a lot of cool things you can do once you have this estimated geometry. Here we're taking the full volume representation and incorporating a virtual object. Handling occlusions properly is not trivial. However, our framework gives you this for free. So from AR to robotics, we think there's a lot of potential applications. Finally, we found that the impact of positional encoding, surprising and really cool. It was clearly helpful in allowing the neural network to learn high frequency functions. So we're currently exploring other applications outside of view synthesis that can take advantage of this trick. Thanks for listening, and we really invite people to go to the website where you can see the videos in full res and hopefully better frame rates.
Terrific. Thank you, guys. That was perfect, and it's super interesting results. David, I'll let you ask the first question.
Sure, I got two questions. So the first is, this looks really powerful, and I'm wondering if you have any thoughts or ideas on applications or that this might enable, like from an industry perspective. And second is, for our attendees, if any of them would love to get this kind of expertise on their team. Is anyone on your group graduating soon?
Let me answer that second question first, and then I'll let these fine researchers talk about the answer to the technical one. So, why, thank you for asking, David. It turns out that Pratul is currently looking for jobs. He's going to graduate with his PhD this semester. Ben will graduate next year. Is also, I'm sure, interested in opportunities. Matt also, Matt is in his second year, but has been very active and very interested in self-driving cars, and has been very active in doing internships in there. So there you go. Fellas, you want to answer that technical question?
Yeah, sure. Am I unmuted? So I think that there's like the obvious applications in VR and AR context. So right now we do have a problem where the method in comparison to something like LLFF, it's much slower. It's about like kind of 1 to 30 seconds per frame. So it's not close to real time yet. But I think like if you were able to boost that up a lot, incorporating this into like various like augmented mixed virtual reality things would be really cool. And then in addition, I think that we were quite surprised at how good the geometry looks if you just look at kind of the learned scene density and not those output colors. So I think there's probably a lot of applications where you could actually do something like this. It gets you a good shape, and you could bake that out as like a discrete grid or as a mesh or something, and take that approximation and use it elsewhere. Those are two things.
Perfect. Okay, great. Listen, I know there's more hands up, and Avide has a question, but I want to get us back on schedule because Mike Jordan actually has a tight window here. So I want him to start. And Avide, if you don't mind, we'll have time for questions a little bit later. I'm sorry to push you on that. Let's see, Matthew, thank you, Ben, Pratul, and Ren for a great talk. If you unshare your screen, I think Mike is ready to come on board. Mike, if you share yours. Abide, you can ask your question in the meantime.
Okay, real quick question. Thanks for the great talk. Does this method work when your point of view, reconstruction point of view changes a lot more drastically than just the small rotations and translations? In particular, what I have in mind is if you have a model of, I have lots of pictures of a building or an interior space, and you want to do that.
Okay. I'm going to ask that we hold off on answering that question to give Mike his full amount of time, but think about it, and then hopefully we'll get a chance to come back to it either through this or email. All right. Thank you, Abide. Mike, you're on. We need to unmute you.
Okay, I'm chatting. All
there
right.
You are.
We're all getting better and better at this Zoom stuff over the years. That's one of the few advantages of this era. So that was a great talk. And I just saw some comments about how great it was. There was like, this is really cool stuff or something. I thought, that's amazing. Even before I started my talk, they're saying it's really cool stuff. But actually, that was for Ren's talk, of course. Ren and Call. Yeah, so I've been very interested in decision-making the last few years. And I tell a little story about machine learning that is a little different than the one that's commonly being told that focuses on pattern recognition. So I think of machine learning as having two main faces to it. One is pattern recognition. The other is decision making. They're pretty different, although they obviously have to glue together. If you think about the pattern recognition thing, you're kind of led to, we've got pretty good pattern recognition, so we can go back to all kinds of classical AI problems and even some nearby problems in computer science and solve them. We couldn't solve them before because we have now data that can replace mappings that were hard to kind of get our hands on before. I'm thinking about machine learning from a rather different point of view. I'm thinking about planetary scale data analysis, systems that make decisions based on data flows, and all the issues that can come up when you start to design systems like that. Kind of think of a factory level instead of kind of an individual component level. So this is a slide I won't go through in detail for want of time, but it's kind of how I start off a lot of my talks these days. This is a kind of a historical perspective on the rise of machine learning, and it's not the end state is deep learning and stochastic gradient descent. It's rather a different end state. So I think of Amazon.com and the industry perspective here, kind of back in the 90s, as kind of a place to just situate this little historical dialogue. You know, the back end, fraud detection, search, and particularly supply chain management. They did this really well in the 90s. Modeling, you know, with huge numbers of computers. They had the, you know, kind of the original cloud, modeling how long it takes to get a ship across the Indian Ocean and having a probability distribution on that and putting that all together in a big logistics computation. And they did that so well, they could serve 1 billion products within a day or two at this point, and it goes on. So that's the first generation. It was machine learning, and it was at scale, and it led to billion-dollar industries. Second generation, I think, was about human side, that a lot of this data was about human beings in these flows and these networks, not just logistics. So the rise of recommendation systems, I think that's also a sort of second billion-dollar industry that arose. I see us now as in the era of pattern recognition on steroids. Speech recognition, vision, translation, then a range of other problems become possible because of data collection and really, really good pattern recognition. But I think that's kind of a phase. That's not an end state. And it's only half of the problem. So I think of not just an agent making a decision or a sequence of decisions like an RL or whatever, but a huge planetary scale interconnected web of agents, data, and decisions involving computing and people and so on. So think markets and think the medical system. The worldwide medical system right now is a system. It's kind of a really bad system, but it involves computing and data and decisions and preferences and life and death kind of issues. It would be great if it were a well-designed system involving inferential decision-making principles. Think transportation, which is in some ways a better such existing system. Think commerce, and think about it, many other domains. Entertainment is kind of a worldwide connected system that we should be contributing to. All right, so now let's take the perspective on decisions. Let's kind of revert to statistics 101. So if you're used to thinking about pattern recognition, you think, oh, decisions, that's easy. I just threshold the output of my really, really good neural network, and that's a decision. Okay, so I'm going to argue, no, that's not the right way to think about it. Think about you go into the doctor's office, and the doctor measures all kinds of things about you, your temperature, your body, your genome, and 40,000 dimensional feature vector goes into the world's biggest neural net that has all the world's medical knowledge in it. All right, and out comes a number on one of the outputs that says if that number is over 0.7, you're likely to have a heart attack soon, and that number is 0.701. All right, is that a decision? Well, no, because even though that's a big neural network with lots of knowledge, it's missing all kinds of things about your particular situation in this moment. You're going to ask questions about your doctor. You're going to want error bars. Is that data that was used to train that network actually relevant to me? Were different kind of people, different kind of machines? Is it old, out-of-date data? So on and so forth. There's going to be a whole dialogue involving your single one decision when it matters. You'll want to do what-if experiments. What if I were to look at the data differently? What if I were to collect this other bit of data? What if you knew something else about me? You're going to rerun things. It's a whole enterprise of its own. It's not the output of a really, really good network. I think we've been kind of led astray by some of the problem areas people are focused on. All right, but that's not even the beginnings of it, because it's never just a single decision. It's sets of decision. Today I'm not going to make just one decision. I'm going to make a range of them, and they all should somehow be good. They may or may not be sequential. They might be batched in various ways. They may be about in different domains. There should be false discovery rate control. All right. But not only that, there are sets of decisions across a network, and they're across time involving people, like I say, planetary scale. All the medical decisions that we made right in this moment around the world somehow should inform each other and interact. So we want to do asynchronous online testing at massive scale. Okay, these are the kind of systems we need to think about building. Now, even more so, there's going to be decisions when there's scarcity and competition. In machine learning and in AI generally, we've not thought about this hardly at all. We've taken a very much, you just build the system, let's make it as good as possible. But then you put it out in the real world, it starts to interact with other decision makers, and there's competition, scarcity, and suddenly things break. Okay, so here's a domain where I started to think about this in the domain of markets. Markets are decentralized algorithms. They can accomplish complex tasks without a huge amount of programming. So they're very complementary to machine learning. They're adaptive, they're robust, they're scalable. They can have a long lifetime. You don't have to keep updating them. They just kind of change and so on. Of course, they're not perfect, and we're going to need new principles in our new data-rich era, computing era. The classical markets were not developed for that era. Okay, so I started thinking about this in the domain of recommendation systems. You all know what they are. It's kind of a pattern recognition scheme, but you want to use it for decision making. All right, they become a commodity. But what if you roll them out in situations where there's competition? All right, so in the first case, like movies and books, there's not much competition. If I recommend to Ren Ng a certain movie or book, and he likes it and picks it, I can send it to him, and I can send it to Pieter, and I can send it to Ken, I can send it to millions of people per day, because I can copy the bits. There's no scarcity. But if I recommend the same restaurant to a whole bunch of people, and a lot of people are using my system, I'm going to create congestion. It's not all people can go to the same place. Same thing about recommending streets to drivers. Also, if I recommend the same stock purchase to a huge number of people, I'm going to destabilize the market, and so on and so forth. So these are the kind of issues that if you're an economist, it's just, of course, you have to think about this. But the people using recommendation systems as commodities are often making these kind of recommendation systems without even worrying about this. They just hope when they put it out there and it's used at scale, it'll somehow do a load balancing, but it will not. It'll actually fail. And so these are one of our major failure points. It's not all that hard to think about fixing this. It's not a machine learning problem. It's not just get better data or do the load balancing yourself on your computer. It's create a market. There should be a two-way market between producers and consumers. For example, diners on one side of the market, restaurants on the other. Drivers on one side of the market, street segments on the other. And, you know, bids are made, maybe an auction set up, maybe a matching is done, and so on and so forth. The difference with classical microeconomics is this is now based on huge numbers of entities on both sides of the market. And moreover, each side of the market does not have a pre-specified set of preferences for the other side of the market. I do not know of all the restaurants in the world which ones I prefer. I've only sampled a very small number. I don't know the path that's best to get to the airport in a town I've never been in, and so on and so forth. So how do you fix that? Well, you have to now bring in machine learning. You add machine learning into microeconomics, okay? And you have to do this with things like recommendation systems. Maybe I haven't experienced all the restaurants in Shanghai, but a whole bunch of people have been to Shanghai, and somehow that information flow over to me as I participate in the market. And similarly, on the other side of the market, they will have to share information so they can make an efficient market. We don't have principles for doing this, all right? So we have to work on this. If you just take classical machine learning and try to throw it into microeconomics, I can tell you there's a lot of failure modes, and similarly the other direction. So this is what I've been working on, and which I'm going to continue to work on for several years. Things like multi-way markets where you have to learn your preferences, recommendation systems merged with multi-way markets, and so on and so forth. So we have a whole bunch of projects on this. And in my short amount of time, I'm going to mention one of them. That's just a kind of, some ways, a thought experiment to kind of get us started. How can we glue together learning principles with microeconomic principles, or really game theory principles? So this is work with Lydia Liu and Hori Amania, students in my group. All right, so my favorite learning problem actually is not stochastic gradient descent or supervised learning, it's bandits. Because in the bandit problem, it's the pure learning problem. I've got K options and I don't know which is best. So I've got to try them out and start to figure out which is best. So this kind of sounds like reinforcement learning, but not really. It's better than that. Really, the exploration is key here. All right, you have to keep exploring options you haven't actually looked at before. And in the reinforcement learning setting, that's often done in an ad hoc way with a greedy algorithm or some kind of a Boltzmann distribution or something. We want, in the bandit problem, you really face this as a first-class problem, and you get regret bounds that tell you how bad you are, even if you're exploring. All right, so a classical one is you try an arm, you get a reward, you try another arm, you get a reward, and you put something like a confidence bound on the rewards, and you might choose arms based on the upper confidence bound. That's kind of a famous algorithm, one of many that has very nice regret properties. All right, so we're going to put that together with matching markets, which is, of course, a famous area of microeconomics. There have been Nobel Prizes and so on, where we have a two-sided market. We have buyers and sellers. And on each side, we assume we know the preferences. Buyers have a list of preferences for the sellers and vice versa. And then something like a Gale-Shapley algorithm is run to find a matching, okay, that has nice game theoretic properties, okay? The problem, of course, is that we probably don't know our preferences on the other side of the market in many of the emerging problems, okay? So we have to experience that. We have to bring in something like a bandit algorithm in the context of a market. So now we have two players. We've got a human and a bear, and they're both playing the game, and they're picking arms, but there's going to now be scarcity, so that if both of them happen to pick arm 2 at some point, only one of them gets the reward. All right, which one gets the reward? Well, the other side of the market has a preference back on us. We don't know that preference, and it may even be stochastic, and we have to figure that out again as part of the learning problem. And that side of the market is also learning its preferences too, based on these experiences, okay? All right, so if I pull the arm and the bear pulls it and I lose it, that's a signal to me that maybe the bear is going to like that arm, and maybe the arm likes the bear. So I better start pulling the other arms more than I otherwise would, and I'll pay a hit here. I'll pay a cost in terms of exploration, in terms of regret, but it's necessary in this problem. And eventually, hopefully, we'll both get an arm which is pretty good for us, and we'll have a form of matching. All right, so I hope you see that that's a problem. There's all kinds of other versions of this problem. Maybe the rewards are different. For us, the rewards are different for each arm, for each person. They could be the same. You could share information, and so on and so forth. So we've studied this. We've defined what we call a bandit market. We've defined specific algorithms here in this market. We've defined the notion of regret. And the regret in this particular example is your reward relative to what a Gale-Shapley algorithm would have if it knew all the preferences a priori. All right, and here's an algorithm which is Gale-Shapley converged with, mixed up with upper confidence bound. We all keep an upper confidence bound on all the arms, and we send those to a Gale-Shapley algorithm, and it makes a match based on our UCB. All right, with that algorithm, we're able to prove a regret bound. It's logarithmic in the number of rounds, which is optimal, and we have an actual gap that depends on how many other agents there are. Okay, all right. In my last, I think, 1 minute, Ken, can you hold up a number of fingers of how many minutes you want me to have left? I could say you.
One.
One. Good. All right, that's what I hoped. Now that you've heard about UCB a little bit, you keep an upper confidence bound on rewards. Either it's a good arm and therefore the bound is high, so you should keep pulling it, or you haven't experienced it very many times, so the upper confidence bound is high because you have high uncertainty, so you should explore it more. So UCB in one idea gets two concepts. That can be applied in many other decision-making realms, and I just want to mention as a bit of dessert here, we've done this with Q-learning. So I'm sure all of you know about reinforcement learning about Q-learning. In line 2, you're here to see the classical Q-learning algorithm plus a bonus, which is the UCB bonus, the upper confidence bound. All right, we have analyzed that algorithm theoretically, and we have shown that it has a certain regret. It's not that common to get regret bounds for Q-learning, for reinforcement learning, and that regret here is square root in T, the number of rounds. And my last slide here is a comparison of all the model-based algorithms and all the model-free algorithms for reinforcement learning when there's been theory done. The model-based cases all get this square root of T regret. All right, and for most of the model-free algorithms, they were not square root of T. They were T or T to the 4/5, and that was kind of evidence that model-free was worse than model-based in a theoretical sense. But when you add UCB and not greedy methods here, your regret goes to square root of T also for model-free. So in that sense, model-free is as good as model-based from a very clear theoretical perspective. All right, so lots of ongoing work on all this. Just let me go back to my top-level comments. There's been a lot of focus, very helpfully, on pattern recognition. But if you start to go out in the real world where there's real consequences, where there's life and death, and there's planetary scale issues, this is not just pattern recognition, folks. This is decision-making in spades. And so we as a community have got to start to face that for high-stake decisions, for explanations, sequences, and especially for market mechanisms. Thanks, everybody.
Bravo. Fantastic talk, Mike. I actually want, when you said how many minutes do I want to give you, I mean, I would give you an hour. If
Thanks, Ken.
Okay, Ren, do you want to pick up the role of respondent?
Sure, thanks. Actually, I was going to ask a question that you kind of partially answered a little bit on this parting comment slide, Mike, but maybe I'll ask it and you could dig a bit deeper. So when you talk about machine learning for decision-making, I think, the current era that we're in, we're seeing a lot of these high-stakes decisions that you're describing. For example, the high-stakes decision of when, a particular area, leadership will ask us to go into isolation, shelter at home in order to try to flatten the curve, for example. And I think that this message that so many of us receive currently really touches on many of the things that you described in decision-making, which is not just about making the technical decision of which way to go, but then on being able to explain that decision and then take the leadership using that explanation to cause others to go along with the decision. Part of that, I think, is on your parting slide, but maybe you want to talk a bit more about how you see ML fit into those different aspects of the decision-making process and its consequences.
Yeah, thanks, Ren. That's a fantastic question. I mean, you expressed it just as well as I can, I think. We could have a long conversation about that. How do you incentivize the data collection to be correct? How do you incentivize people to send the right data? How do you incentivize exploration? How do you try policies out? How do you do that when there is coordination needed? And basically, I just don't think we have the tools mentally to do this at this point. It is not about, hey, I know how to do this, and let's go build the factory that does it. It's like we're in the era of chemistry in the 20s, where we knew how to kind of put ingredients together in test tubes and make a few things, and we knew the quantum theory. We were really sophisticated, but we could not go build a factory. If we did it, we didn't know the thermodynamics at that scale. We didn't know all the things that could go right or wrong as fluids flowed, at multiple scales. So, as smart as we are, I think that we have to admit some humility here. We don't really know. You know, that said, things are going on in the current moment, and I think that we can, you know, that we do have already, you know, game theoretic machine learning ways of thinking. Machine learning, though, is part of a dynamical system. When I start to gather data, it will have impact on what happens next. The people that are trying to get a ranking out of that will change it and game it and so on. So, you know, we need to kind of start to step up and have humility that we don't know how to solve the problems, but nonetheless, here are the problems, and here's the ones that we think we can face now, and here's the research agenda for the next 20 or 30 years. And it definitely involves everything you said very elegantly. And I think that, yeah, the background of what's happening right now, you know, definitely this is a big part of it. It's learning about the biology and the epidemiology and all that, but it's learning how to make all the good decisions and collect the right data at the right time so it's available. This is all new stuff, and we're being triggered now by, in some ways, almost luckily.
Super. Okay, thank you so much, Mike. I know you have to run. Dan, are you here? Dan Klein? I think he's here. Dan, you can unmute.
All right, can you hear me okay?
Perfect. Thank you, Dan.
All right.
Thank you, Mike, for a great talk. Dan, I feel sorry for you. You have to go after Mike, but do your best.
Someone's got to do it.
Someone's got to do it.
Okay.
I had to go after Ren Ng. That's just as hard.
All right. All right. Well, it's great to be with everyone virtually. I'm going to be talking a little bit about modularity in natural language processing and some work in our group that's been in this direction. So first hide this. So if you've been watching recent progress in natural language processing, there's really been some massive successes on a very wide range of tasks. And those improvements have come from a bunch of factors, actually. Some of it has been better architectures. Some of it has been bigger models, just training larger models on more and more data. And some of that has been from, in natural language processing in particular, from techniques such as pre-training, which have really given us across the board advances. And so this graph that you see on the right here in particular, I like this graph. This is from Slav Petrov. This shows the state of the art in syntactic constituency parsing in NLP over about the past 10 years. What I like about this graph is the leftmost bar was the Berkeley parser in 2010, and the rightmost bar is the Berkeley parser from today. And as you can see, there's just been steady progress from a variety of factors across a variety of labs. So I'm going to dig in today a little bit about where these successes have been coming from. But really, it's, you know, from far out, it's been a massive success story. However, there's also some major limitations, again, not only in natural language processing, but in AI in general. And even though the neural models we use and the ways in which we use them have brought about great increases in accuracy, there's still some major limitations. So what's wrong with the kinds of neural models we build today? Well, there are a couple issues. And again, this is not just my lab by any means. It's not just NLP. It's really across the entire industry. We see the following things. One, these models we build today are extremely data hungry. They require huge amounts of data to learn to do the task of interest. The second thing is the models are single purpose. That means that you take all of this data to teach the model how to do some task. And when that's all done, they can only do that exact task that was embodied by that data, as opposed to people who are able to take their ability in one task and apply that to other situations and other configurations of the environment. The third thing is that the models we build today are monolithic. And that is, we build these very large models with lots and lots of parameters. And not only can it be difficult to tell what's going on inside them, but they can't be decomposed. And that means they can't be reused. And all of these limitations are consequences of a lack of modularity. If you think about learning to learning to program a computer, one of the first things you learn is you don't write one big script that gets bigger and bigger and bigger. As things start to get more complex, you break them into, you use abstraction and composition to break them into pieces that can be not only understood in a modular way, but reused and improved in a modular way. And this lack of modularity has consequences, both for the ability to take the models we build and use them in new settings, but also in terms of the modularity of how people work on these things. Each person can't take one part of the code and improve it as long as it's all completely coupled. So what I'm going to talk today a little bit is about some kinds of modularity that you might be able to bring to these models and how that's been working out for us. So in fact, in natural language processing, one long-standing goal we've had is something that could really be called knowledge modularity. And that's the goal of being able to take some domain general knowledge from one source and use it to solve specific problems elsewhere. People have been trying to do this for a long time, but one classic instance of trying to meet this goal was the Brown clustering work in the early 90s, which was basically an attempt to do what pre-training does today. It was an attempt to say, look, I have my task, and in my task, there are plenty of things going on, but there's also just a lot of words that I'm not going to see in my relatively modest amount of training data. So it would be lovely if I could go to some very large collection of training data and learn something like gray and silver are both colors and they behave similarly. So if I haven't seen both of them, that's fine. Once you see one color, you know how they all behave for many tasks. So that idea that we could capture synonymy and lexical variation on one corpus and then import that into models on another corpus, that was a kind of knowledge modularity that has seen on and off success. It's usually helpful, but it's been hard to really make it work. And that line of work really extends right through to the current day with word embeddings and things like word2vec or glove vectors, where we don't put words into clusters, but we still characterize them with representations that are trained on one large general purpose setting, and then we use them for our specific tasks, hoping that the lexical variation, things like synonymy, is abstracted away, which renders our task of interest easier to learn. So once you learn that good and great and enjoyable are all the same, all you really have to learn for sentiment analysis is that when you see one of those words, it's a good thing. And if you see the others, it's a good thing too. Now, this isn't perfect. And in particular, it was very difficult to get word embeddings or word clusterings to improve across the board. And that's because we already in NLP use relatively big data sets. And so we've seen a lot of the words, and lexical variation alone was not actually the bottleneck. So the key thing that's really unlocked the modern era of training on one data set in a general purpose way, usually using autoregressive language models, and then moving to some specific task and getting significant accelerations in accuracy or sample complexity. The key idea there was to embed not words, but context, because although there aren't that many words, there are quite a lot of context because that's sequences of words. Using embeddings of context for other tasks has basically just transformed the accuracy landscape in NLP. So for example, there's been a recent explosion of pre-training work, lots of Sesame Street characters involved, and you can see on the left accuracies on the GLUE task set, which is a collection of sentence level processing tasks, has just gone up and up and up with largely the same kinds of models, but tapping into more and more sophisticated pre-training and larger pre-training. So you can make these models get better and better and better by importing knowledge trained from elsewhere. So what does that knowledge look like? Well, we can check to see what's in a language model. And we made some of this precise in our work, but I'll just give you an example from a sample from a GPT-2 model from the Talk to Transformer site. So I primed it with, welcome to the 2020 Berkeley AI Research Workshop. I'll be discussing our recent work in NLP, and then I let the model take over from there. And the purpose of this is not to let the model give my talk for me, though maybe we're getting close to that, but it's to see what kinds of correlations and knowledge are captured in the parameters of these autoregressive language models. So here we go. Welcome to the 2020 Berkeley AI Research Workshop. I'll be discussing our recent work in NLP with this talk and some more fun topics like natural language understanding. Please note that this talk is not intended for other researchers. I just wanted to give a taste of the basic skill set I've developed at NLP at Berkeley. MIT and Berkeley, they are huge. The national labs are recruiting and there are lots of jobs. But in a neighborhood a couple miles from my apartment in the Bay Area, I have only one job, which is to teach my students and postdocs about artificial intelligence and NLP. So there's some amazing stuff in here, and there's a lot of stuff missing. You can see the kinds of correlations. It's syntactically very well formed. So we know whatever there is about syntactic coherence is pretty well captured in these models, and we can expect to see downstream tasks accelerated insofar as they no longer have to learn that. There's also some coherence here as far as style. This is all relatively informal, but there is a big shift between the paragraphs from a talk overview to a little bit of a little bit more of a blog post style. You'll also notice there's long distance correlations in topic and in lexicon. So Berkeley appears at the beginning and then it shows up at the end. AI triggers artificial intelligence. NLP pops up here and there along with NLU, which is a related term. So at some level, what are we doing? We're learning which words, which contexts are similar. We're mixing and matching from data that we've seen on various levels of abstraction, and that's really powerful. Now, is this knowledge modularity? It's knowledge of a certain kind. It's certainly not complete. So here's another one. Welcome to the 2020 research workshop for AI, which has reached a point where it is a force multiplier for creativity and scientific insight in the field. This talk will focus on what it is we take for granted and why we might be missing that. Links to the paper in which this talk appeared is below. So I clicked on that paper and it turns out it's about cluster galaxy properties. So obviously what's happening here is not a complete deep understanding of everything in the world, but it is a certain amount of linguistic correlations that are quite sophisticated being captured. And what that means is it means we can very easily tap into these kinds of models for pre-training, where downstream in the model architecture is going to be our specific task. So for example, if I want to do syntactic parsing, where I'd like to put a sentence like she enjoys playing tennis into nested bracket groups like this, we might be able to accelerate that with this kind of a technique. Now, classically, syntactic parsing was all about grammars and correlations between output symbols. Recently, though, there's been more of a move to directly predicting the output symbols. So for example, I could look at enjoys playing tennis and try to directly predict that that's a verb phrase. On what could I base that decision? Well, if I sort of encode this sentence, I'll see that there's a pronoun to the left and there's a verb, and this is a verb at the start of the sentence. And so that position is sort of characterized by its linguistic context. The end of the span is also characterized by its linguistic context. And so I have a bunch of information on the basis of which I could conclude that this is a verb phrase. So there are some issues to sort out, like there are certain spans cannot both be in the tree at the same time. So there's a bit of structured machine learning here that I'm not going to get into. But to a first approximation, I have to look at a span in a sentence and make a decision based on its syntactic properties. And that is a kind of thing which we can do much better than we used to based on just the sort of architecture and structured learning here. We can get up to about 92 F1 as an accuracy measure, but we could also take those kinds of pre-trained encoders, insert them in this pipeline in an appropriate way, and let that pre-training abstract away from all of the syntactic stuff going on to the left and the right. We could also sort of try this with different architectures like a transformer architecture. And what we found is that although you can still get quite competitive results without pre-training, of course, as people have found in task after task, the bigger a model you plug into your encoder, the more information is imported and the better you do. Now that's exciting because those accuracies are sort of more than halved from a decade ago. And this works also multilingually. So across a very wide range of languages, we can right off the bat have a great reduction of error rate in our linguistic analysis based on this kind of pre-training. However, it is a very, while this has been a really great step forward in terms of our ability to take information from one data set and apply it somewhere else, it's not quite true modularity, or rather it's not modularity that's as efficient as it could be. We still have to couple, we still have to take the model that was trained and do fine tuning on that. This is less like reading a book to get information from others' experiences into your brain in a sort of modular and declarative way. And it's more like grafting two brains together and giving them a chance to sort of impedance match. which is a kind of modularity, but weak. You could imagine a stronger kind of modularity, which we've also thought a lot about here in the Berkeley NLP group, and also in collaboration with folks like Trevor. And you could imagine a much stronger kind of structural modularity, where we build systems that actually break into pieces that can be reconfigured in explicit ways. So for example, if I want to answer how many...
I'm sorry. I really don't want to interrupt you. We just have probably a minute left. If you
That's all I got. I got 2 slides.
Oh, perfect.
Okay. Where was I? So we might want to build a system where we can say how many black cats are there, and have one module that, say, finds a dog, and another module that describes where the dog is, and then string those things together in a dynamic way. That would be a sort of more explicit kind of modularity, and this is something that I think is going to become increasingly important as we in NLP and beyond build more and more complicated neural systems that have to mix and match to do multiple things, and not just train single monolithic systems that do the one task on which they were trained. That's all I got. Thanks so much, and it's been great being with all of you virtually today.
Terrific. All right, great. Thank you so much, Dan. I'm going to ask a quick question for you, which is related a little bit to some of the topics that have come up. Like David Wagner has talked about security and adversarial situations. So one thing I'm curious about is when we're training on these very large corpuses, for example, Google can train on all of our email, for example. What is there a danger that you may be able to call up the beautiful example you just gave, where I could then utter into such a system something like, my name is Ken Goldberg and my social security number is blank, and that it would pop up those kind of answers, like it would be exploitable in that way. Is that a concern?
Yeah, it's definitely a concern. So in addition to sort of a differential privacy style concerns, where you want to really think about what has been buried in those parameters, to a certain extent, there's some evidence that although there's generalization happening, a lot of memorization is happening as well. And so you can worry that the system will regurgitate information that you might not want it to. But there's subtler things too. You build systems like this and they exhibit biases that you might not want, that are driven by the structure of the data that they learn even in aggregate. And that's in some ways might be even harder to limit. And then there are other issues on the security side. So another project that's going on in my group right now is looking at adversarial examples, and how easy is it to insert an example where it's likely to be crawled by a web crawler, which might then go on to poison a model downstream and cause it to exhibit errors that either at random or targeted errors that you might want that system to maliciously do. So a lot of that's with my student Eric Wallace, and I think there is just a huge area now of NLP intersecting security and concerns of exactly the kind you're raising. So thanks, that's a great question.
Excellent, thank you very much, Dan. Okay, great. I know Ren has a quick question, and Stuart, I think you're coming up, so I want to thank you, Dan. If you unshare your screen, Stuart will pull in, and Ren, do you want to jump in with a real quick question?
Oh, sure. So Dan, so many of us in education spend a lot of time teaching our students to write well, like, thesis statement, topic sentences, high relevance and all the evidence to the topic sentences, and then the thesis statement. Is this something that is learned in these language models? I'm curious, or do you try to encode for this when you try to teach a machine to write well?
That's a great question. If you ask this question like 10 years ago, language models really captured local syntactic and semantic coherence, but none of these longer term rhetorical or discourse structures. One of the big changes in modern language modeling is that rather than focusing on the internal structure in a sentence, you focus more on longer distance correlations. And so a lot of those things, topicality, support, and then conclusion, a lot of that is actually captured. And captured quite well. And in some sense, that is more templatic than a lot of the information that goes in between. And so those things are captured fairly well.
Okay, super. I have to say, it's a very rough job. I feel like Procrustes here. I have to chop these talks down to these 15-minute slots. So apologies for that. We'll turn to Stuart. We are running 9 minutes now behind schedule. So Stuart, we'll give you your full 15 minutes. Please begin.
Minutes on the schedule, but that's okay. I'll try and do it more quickly. And I would normally make a joke about being between everybody and lunch, but of course everyone's already eating their lunch while they're listening to this. So here's a quote from Alan Turing. It seems probable that once the machine thinking method had started, it would not take long to outstrip our feeble powers. At some stage, therefore, we should have to expect the machines to take control. So what I'm going to talk about is how not to have this happen. And I just wanted to give you a reality check. So people are very excited about deep learning. Here's actually one of the more impressive results of deep learning. This is reinforcement learning for quasi-humanoid robots, which basically wake up in the morning. They're newborn babies. They are totally unable to coordinate their limbs. And then within a couple of hours, they're out in the garden playing soccer. As you can see, the blue guy is pretty good at scoring. Most of the time he wins. He's up 7 goals to 3. And this was a very impressive result that came from OpenAI. My student, Adam Gleave, and several other people in the group looked at this and wondered, how robust is this performance? And so they came up with a new policy for the red guy. So they left the policy for the blue guy exactly the same. So the blue guy is trying to score goals. We're just going to change the goalkeeper to try to stop the blue guy from scoring. Okay, so here's what the red guy does. He just falls over on the ground and waggles his leg. And now the blue guy is completely unable to score. This is exactly the same blue policy that you just saw scoring goals again and again and again. But now, most of the time, he either kicks it straight at the red guy or he just falls over and doesn't even get to kick the ball at all. So what you can see is, in fact, that the blue guy was not kicking the ball in order to score goals. Probably it was more like they had learned to tango together. And as soon as one partner in the tango stops dancing, the other one doesn't know what to do anymore. So we are over-interpreting the capabilities of AI systems. Notice this is not a classical adversarial example. We're not corrupting any of the data here that's reaching the blue guy. We're just having the red guy do something that he's physically capable of doing. It's just a different thing than he normally does. So I think we probably are going to run into some plateaus with the purely data-driven deep learning approach. And Dan has implicitly agreed with that by talking about the need for knowledge and modularity. And Mike has talked about the need to focus on decision-making and the structure of markets and so on. But this is not a new point, right? So Francois Chollet, who's one of the authors of one of the main deep learning toolkits, wrote a textbook on deep learning, and he says, look, be honest, many applications are completely out of reach of deep learning techniques, and instead we should be looking at models closer to general purpose computer programs. And that's a reasonable point, right? Why are we using circuits, which we haven't used in the software industry since before the Second World War, right? Back in the 20s or even the late 19th century, arguably, we used mechanical circuits or then later on electrical circuits to do computations. But we stopped doing that once we had Turing machines and we started writing programs. So why are we back to using circuits? It's kind of ridiculous. So fortunately, there's an area called probabilistic programming, which has been doing that for more than 20 years. It originated from a couple of students in my group at Berkeley, along with David McAllister in a paper in '97. And now it's reached a level of about 2,000 papers per year being published, with dozens of applications with several large groups in the major industry players. So if I had to guess, I'd say that some merger of probabilistic programming with deep learning is going to be the next wave of AI. So whatever happens, I think in the long run, we're going to have to assume and act as if this is going to take place, that AI systems will eventually be making better decisions than human beings in the real world. The alternative is to say, okay, we'll fail in AI. In fact, we're just going to run out of gas. And some people in the AI community are now arguing this after 70 years of arguing that AI will succeed, and all of you skeptics in the philosophy community and the math community are all just idiots. Of course, we're going to eventually succeed in AI. Some in the AI community are now saying, actually, no, we're going to fail. And this is not really feasible as a way of managing our affairs. So Turing's point is really, we're going to build these entities. They're going to be more powerful than human beings. How do we retain control over those entities forever? And that's, I think, a question that is worthy of our attention. If you don't agree with that question, or you don't agree with this, this line of thinking, there's a paper in IEEE Spectrum which thoughtfully lists 15 or 20 arguments that people have made for why we shouldn't pay attention. And you're welcome to come up with new ones or to revive some of those that have already been refuted. And I'm happy to have that, that discussion. So let's see exactly what the problem is, right? We look at the standard model for AI, right? And here, this is basically what happens, that the human says, okay, here's what I want to do. Here's the objective, you know, maximize this expected sum of rewards, whatever. And we devise machines that basically are able to carry out this task. And so off the robot goes and figures out how to maximize this sum of rewards. And this is not just AI, right? This is control theory where you're minimizing cost functions. It's statistics where you're minimizing loss functions. OR has exactly the same, the sum of rewards formulation. Economics, it's you know, a social welfare function, or you know, quarterly discounted profit stream, or whatever it might be. And we've known for thousands of years, actually, that this is a really bad engineering model. It's a really bad methodology because we cannot specify the objective correctly. This is the point of the King Midas story. This is the point of the genie who gives you 3 wishes, and your third wish is always, please, could you undo the first 2 wishes because I messed up. And the problem with this, in a nutshell, why is this a bad engineering approach? Because the smarter the AI, the worse the outcome for human beings. The AI system will end up messing up more of the world in order to optimize the objective function that you specified incorrectly. And we can see this in social media. So when you set up learning algorithms that control what billions of people spend hours of every single day reading and watching, then that's a very powerful platform. And they designed that platform to optimize initially some metrics such as click-through. And you would think, oh, well, that doesn't sound so bad, right? Because clicking is what people want to click on. So the systems will learn to send people what they're interested in, right? Sounds good to me. But in fact, that's not what happened. What happened is that the systems learn to modify people to be more predictable, because a person for these algorithms is a sequence of clicks. And that's enough state for the algorithms to learn how to modify people and turn them into more predictable clickers with the results that we all know about. So I think sort of psychoanalyzing the history of AI, right? We started out with a perfectly sensible observation, right? In the 1940s, we had come to a pretty much a consensus conclusion that the notion of intelligence we were interested in from an engineering point of view was rationality. The fact that actions can be expected to achieve objectives. So we took this notion that economics and philosophy had provided us with for what we mean by intelligence in humans, and we copied that to machines. We said, this is what we want our machines to be like. And of course, we have to specify those objectives because they don't have them. But that is what we're going to create. We're going to create objective optimizers and then let them go. And I think that was the mistake because, in fact, we don't know how to specify the objectives completely and correctly. So really, the objectives are going to be in us, and the machines are still going to be obliged to optimize them, but the objectives are not going to be in the machines. And this is a more complicated problem, but it's not an unsolvable problem. It just turns out to be a more difficult and actually a much richer theoretical framework for designing AI systems. And I've summarized this in 3 principles. The robot's goal is to satisfy human preferences. The robot knows that it doesn't know, so it has explicit uncertainty about human preferences. And then there's a conduit through which information flows to the machine. Sort of bits in some form or another have to flow from humans to machines to give evidence about the preferences, and that evidence comes from human behavior. Every choice that humans make and have ever made is evidence about our preferences. When you set this up formally, it becomes a game theoretic formulation. We call these assistance games with human and machine players. And the nice thing about these games is that the smarter the AI, the better the outcome for human beings. So if you want to find out more about it, there's a book that came out in October called Human Incompatible. This is for the general public. We also just finished the 4th edition of the AI textbook, which incorporates some of this material, although not all that much, unfortunately, because not all that much is yet known about the new framework. So mathematically, right, we could set up the simplest kind of game with one human, one machine. The human has some preferences theta and is acting according to those preferences. And the robot has exactly the same payoff, theta, but doesn't know what it is. So it has some prior over theta. And then in the course of the game, at runtime, information is flowing from one to the other, and the robot is acting accordingly. And there's a whole sequence of papers going back to NIPS 2016 describing this. And when you look at the equilibria, very interesting things happen in the solutions to this game. So first of all, the human is incentivized to teach the robot. The robot can learn from that teaching because it understands the teaching behavior as an equilibrium of the game. So there's a kind of coded communication that can occur between the human and the machine that both of them can understand because it's a solution of the game. The robot can ask questions, will ask permission. So before doing anything that would change part of the world that that may or may not be desirable to the human, the robot has an incentive to ask permission because it doesn't want to mess up things that the human cares about. If the human is giving instructions, the robot defers to the human in the sense that it interprets those instructions as further evidence about human preferences. It allows itself to be switched off, which a classical machine optimizing a fixed objective generally will actually prevent instead of allow. So what this means is that when we wanted to write the 4th edition of the textbook, we basically said, okay, well, everything we told you in the first 3 editions is wrong. And here's how you should think about AI. But unfortunately, the technical content of chapters 3 through 25 is mostly the same because we haven't yet redone all of that research and developed all the algorithms and all the applications and all the theorems for that. So this is our goal going forward, is to take essentially each kind of AI system that accepts a fixed known objective and then redo that kind of AI system to allow for uncertainty and, really importantly, and some pipeline, some form of communication with the human who actually has the objectives. The one area where I think we're okay actually is in perception. Perception in the form of interpreting inputs for then subsequent decision making by some other part of the system. If you're doing end-to-end perception, namely, for example, you're perceiving an image and then making a decision directly, for example, even a decision to display a classification on a screen or on a website, and certainly a decision to move the steering wheel in a self-driving car, then again, perception has the same problems that we need to specify the objective. And I'll illustrate that in a second. but as a subsystem of a general purpose decision-making system that is correctly formulated, the better the perception, the better the outcome is going to be. So let's just look at that case, right? So image classifications is something that everyone is doing these days. And when you do statistical learning, you're trying to minimize some loss function. And almost everyone in practice is using a uniform loss matrix. In fact, they're not even thinking about the loss matrix at all. And in all of the competitions, one error costs just the same as another error. So misclassifying a Norfolk Terrier as a Norwich Terrier, which are two of the ImageNet categories, is just as bad as misclassifying a human as a gorilla. Now, Google Photo found out that misclassifying a human as a gorilla is a really bad idea that cost them a vast sums in public relations, damage control, and goodwill, and difficulties in recruiting minorities, and all kinds of other things that messed up their business. So what are you going to do instead? Well, what is the loss matrix? Well, there's about 20,000 categories in ImageNet, so there's a 400 million entry loss matrix, and nobody knows what it is. And certainly, you know, Google Photo didn't think to start writing it down. So you're going to have some uncertainty about what the loss matrix is. That's a very complicated prior distribution. We don't yet even really know how to structure that prior. So there's lots of research to be done just on that topic. And then what does the algorithm look like? Well, it's a more complex algorithm. It's interactive. It's going to be able to classify some examples because it knows enough about the possible costs of error. In other cases, it'll say, I don't know. And in fact, Google Photo right now says, I don't know, whenever you show it a picture of a gorilla. And so there's a nice bunch of PhD theses to be done right there. Here's another example, right? So the typical AI research lab mobile robot task, okay, let's get our robot to fetch the coffee. That goal, fetch the coffee, had better not be the life's mission of the robot to be achieved at all costs, right? And as Norbert Wiener pointed out, we've only been protected from these specification failures by the fact that our machines are so stupid. A machine that really had fetched the coffee as its life's mission and could figure out that one way of failing would be being switched off, for example, which could happen by some human coming along, someone perhaps wanting to take that coffee away. The system is going to take preemptive action, up to and including neutralizing all the people at Starbucks just to make sure that the coffee mission is satisfied. What it really means actually is not this is your life's mission, but what it means is all other things being equal, I would rather have coffee than not. So this is a much more minimal meaning, minimal interpretation of the semantics of these kinds of requests. This goes back to actually von Wright in the early 70s. And it means that the kinds of behavior that your AI system should be exhibiting is what we call minimally invasive, right? So that if there's a way of getting the coffee that doesn't change anything else, then that's a perfectly reasonable thing to do because you have this caterers paribus semantics for the request. Otherwise, if the coffee is really expensive, then it's quite reasonable that the robot should ask you, do you want to spend 15 euros on a cup of coffee at the Georges V? My student Rohan Shah in an iClear paper in 2019 proposed a model where we assume that the world is not in a random state, but the world is actually in a state that you could think of as sampled from the stationary distribution that results from the behavior of lots of rational agents. And in that case, you have an incentive not to mess with it. If it was purely random, there's no difference a priori between doing nothing and doing something, right? Because doing nothing is just one of the actions you could do. And it's just as good as any other action a priori. But if the world is something that's been messed with by rational agents already, then you should leave the world as it is, and that's a better choice. It's also worth pointing out that even if you have absolutely no information about human preferences, you can still help humans by expanding their choice set. So for example, if the human's forgotten their password and you can tell them their password, which is sort of, think of that as a zero cost action, that enables them to do a bunch of stuff that they couldn't do otherwise. And then whatever their preferences are, you will have benefited the human by expanding their choice set. So there are, in fact, many cases where, even in the face of radical uncertainty about preferences, machines can be useful. In addition to redoing all the different subfields of AI to accommodate this, this new framework, there's two very important kinds of research that we have to deal with. One is imperfect.
I'm so sorry to interrupt you, but this is great. I gave it extra 5 minutes because you're absolutely right. We did have you allocated for 20, but we're almost out of that time. So I just wanted to, but I mean, I so apologize for having to cut you short. Or keep going.
No worries. I'm almost at the end. So one is dealing with the fact that humans are imperfect, so their behavior is not a perfect reflection of their underlying preferences. And in fact, if you read, for example, Danny Kahneman's work, you'll see that human preferences are highly unintuitive. For example, they certainly don't add up over time in the way that we think of rewards as adding up over time. There are complications from memory, from expectations. We're uncertain about our own preferences, and our preferences are plastic. We want to avoid machines that modify our preferences in order to satisfy them, and so on. Another set of research questions comes from the fact that there are many humans in the world, and this is obviously a point that the social sciences, political science, sociology, economics, and so on have been struggling with. This is their raison d'etre. So those are some of the questions that arise when you start thinking about acting on behalf of many people. So I just want to mention one result that was in NIPS 2018, when you got one robot and then many humans. And there's a standard theorem going back to my late colleague, John Hassani, saying that Pareto optimal policies on behalf of many humans all optimize a linear combination of the preferences of the individuals. And that theorem basically has to assume a common prior among all of those humans. And if you know any humans, you know that we don't have a common prior. So what do you do about the fact that people may have different beliefs about the future? It turns out that you get a very, in some sense, counterintuitive generalization of this theorem, which is that all Pareto optimal policies have dynamic weights for the preferences of the individuals, where your preferences are weighted more if your prior belief turns out to be true. So it's directly, the weight is directly proportional to the likelihood that your prior assigns to the actual sequence of events that unfolds. And this might sound really weird, because now we're basically going to reward the people who are right and we're going to punish the people who are wrong. And in fact, we'll do that exponentially. But it turns out that everyone a priori will agree to this policy. They prefer it over the fixed linear policy because they think they're right, right? And this is sort of an unavoidable fact about decision-making on behalf of multiple people. I think I'm going to skip over altruism, indifference, and sadism, just to say, so sadism is where one person gains utility from the suffering of others. So we can think of this as having a caring factor that's negative, how much one person cares about the well-being of another. And Hassani said in '77 that we should simply zero out those factors. So when the machine is operating on behalf of n humans, and some of those humans are sadistic, then we shouldn't include the preferences of those humans to cause suffering for other humans. And that sounds fine. I think most people would agree with this one. The problem is that, in fact, when you look at our relative preferences, and sociologists have, in fact, for more than 100 years now, have pointed out that a huge fraction of our overall preference structure is based on relative well-being. That not because you have a shiny car, but you have a nicer, shinier car than somebody else. Not because you have a Nobel Prize, but because the Nobel Prize says that you are smarter than everybody else. That's why it has value to you. And if you look at relative preferences, they function exactly like sadism. They put a negative term on the well-being of other people. If you zero out all of those relative terms, you're making a huge change in our society, and we have to think about that change very carefully. So, to summarize, I'm arguing that we can have provably beneficial AI. We don't have to destroy the world if we don't want to. And this type of AI is actually a desirable kind of AI. It's the way you should be building AI systems, because it will do what people want. It will avoid cooking the cat for dinner because the kids are hungry. And this is not about AI safety. This is about how to do AI the right way. And there's lots of research to do, and I will stop there. Thank you.
Fantastic, fantastic. Thank you so much, Stuart. We do have a minute. Well, I think there's just so many questions, and you've raised, and actually, it's so interesting in a way that your talk goes back to Shankar, to Alison, to Mike's talk, and interleaves for so many connections. And what I'd like to do is postpone quick questions now for the office hours, which we have starting at 1:30. And Stuart, I see that you are available for the office hour then. And I also want to note that we have office hours for almost all speakers today, except for Claire, Mike, and Dan, who can't stay, but the others will be here.
And Shankar.
And Shankar, I'm sorry, okay. And also Abide Zakor will be joining for an office hour. And I'll just describe what we mean by this, which is that we're going to create we have separate Zoom meetings set up for each of these, for each of the speakers. And Angie's going to post in the chat room the links for the Zoom, those meetings. And then, and we're going to try to aim for those to be about half an hour. But then you can go in and just ask questions, have a discussion with the faculty members there. I also want to ask, as many will note, that tomorrow we're going to start again, and we have a full day schedule starting at 10 a.m. And Kurt is going to be it's going to coordinate, and we'll do the similar format. We'll have 2 hours approximately of talks, or 3 hours of talks, and then office hours again. So we're finally able to get to lunch. I want to thank all the speakers for absolutely stellar presentations today. And we will shift over to the lunch, and Angie will post on the chat room, and also a link to where we can get information about the Zoom meetings afterward, the office hours. Okay, great. Thanks, everyone.